Each star in the night sky sparks a question. What secrets do they hide? This documentary takes you on a journey through the mysteries of the universe, where the extraordinary is every day. Discover how galaxies form, stars live and die, and explore distant planets that might host life. The origins of our universe are framed by several compelling scientific theories, with the most prominent being the Big Bang theory. This concept suggests that the universe began as an extraordinarily small and dense point, often referred to as a singularity. Around 14 billion years ago, this singularity underwent a colossal expansion, releasing immense energy and allowing space-time to unfold. Within moments, it transformed into a hot and dense state full of basic particles. As the universe expanded and cooled, these particles began to combine, leading to the formation of simple elements like hydrogen and helium. Another significant theory is cosmic inflation, which posits that immediately after the Big Bang, the universe experienced a period of rapid expansion. Imagine blowing up a balloon. It starts small and then expands swiftly. This inflationary phase would have minimized fluctuations, providing the uniformity that we now observe in the cosmic microwave background radiation, the afterglow of the Big Bang still detectable today. In recent years, the concept of multiverses has gained attention. This theory implies that our universe might be just one of countless others, each potentially with its own unique laws of physics and properties. It raises fascinating questions about what lies beyond our observable universe and if there are other realities that exist in parallel. Each of these theories contributes to our understanding of how the universe came into existence, building a complex picture that combines evidence from cosmic background radiation, the abundance of elements, and the dynamic motion of galaxies. With ongoing research and new discoveries, our understanding continues to evolve, shedding light on the profound mystery of where everything began. The Big Bang theory is a fundamental concept in understanding the universe's origin and how it has evolved over time. It proposes that around 13 billion years ago, the universe began as an incredibly hot and dense point, often referred to as a singularity. Imagine a balloon that is completely deflated. Everything, space, time, and matter, was once compressed into that tiny dot. As the universe started to expand from this singular state, it was like the balloon gradually being inflated. Even though this expansion took place in all directions, it didn't mean that matter was flying into empty space. Instead, space itself was stretching, pulling galaxies away from one another. This means that every galaxy is moving away from others, and the further away a galaxy is, the faster it appears to be receding. Observations support this theory, such as the redshift of light from distant galaxies. When light from these galaxies reaches us, it shows a shift toward red, indicating that they are moving away, similar to how the sound of a siren becomes lower as the emergency vehicle moves further away. This observable fact is a key piece of evidence for the continuous expansion of the universe. As the universe expanded, it also cooled, allowing for the formation of atoms, stars, and galaxies. This expansion is not slowing down, but rather accelerating due to a mysterious force known as dark energy. Think of dark energy as an invisible agent pushing on the fabric of the universe, causing it to stretch even faster over time. Thus, the Big Bang theory brilliantly encapsulates the cosmic journey from a hot, dense beginning to the vast, complex universe we observe today, always expanding as it unfolds across eons. The concept of a multiverse suggests that our universe is just one of many, possibly an infinite number, of universes existing simultaneously. Each universe within this vast collection might have its own distinct laws of physics, dimensions of time and space, and potentially even different forms of matter. This idea stretches the imagination as it implies that there could be universes where circumstances are unique, from slightly different physical constants to entirely new concepts of reality. Scientists explore the possibilities of the multiverse through various theoretical frameworks, primarily drawn from advanced theories in physics, such as string theory and cosmic inflation. For instance, string theory proposes that the fundamental components of the universe are not point-like particles, but rather tiny, vibrating strings. This theory lends itself to multiple dimensions beyond the familiar three, potentially leading to various realities. Cosmic inflation, on the other hand, describes a period shortly after the Big Bang when the universe experienced rapid expansion. Some interpretations suggest that this inflation process could lead to the creation of many isolated bubble universes, each forming its own distinct properties and histories. To investigate these theories, scientists rely on indirect evidence and mathematical models rather than direct observation. By studying the cosmic microwave background radiation, the afterglow of the Big Bang, researchers look for anomalies that might hint at the influence of other universes. Other methods involve exploring the implications of quantum mechanics, where certain interpretations suggest that every possible outcome of a quantum event creates a branching universe. In this tantalizing landscape of ideas, the multiverse remains a subject of intense debate and speculation among physicists. As they delve deeper into the fundamental laws governing our universe and beyond, the multiverse concept challenges our understanding of existence itself, prompting us to ponder not just where we are, but how many places might exist in the vastness of reality. Galaxies, the vast cosmic islands that contain stars, gas, dust, and dark matter, begin their journey in the earliest moments of the universe. Shortly after the Big Bang, the universe was a hot and dense place, gradually expanding and cooling. Over time, tiny fluctuations in density led to areas where matter began to cluster. These regions, often filled with hydrogen and helium gas, served as the seeds for galaxy formation. As gravity pulled more matter into these dense regions, the gas began to collapse and form structures. Imagine taking a handful of cotton balls and compressing them. They gather more cotton as you squeeze tighter. Similarly, as gas concentrated in these areas grew denser, it began to form stars. These stars, sometimes in clusters, interacted through gravity and radiation, leading to complex processes that created more stars, supernovae events, and even black holes. Galaxies can take on various shapes, spiral, elliptical, or irregular, depending on their composition, the dynamics of their star clusters, and their histories of interactions with other galaxies. For instance, spiral galaxies often have beautiful arms made of stars and gas, while elliptical galaxies appear more rounded and feature older, redder stars. The significance of galaxies in the universe cannot be overstated. They are the fundamental building blocks of the cosmos and act as laboratories for cosmic evolution. Each galaxy provides its own unique environment, influencing star formation, the life cycles of stars, and the chemical enrichment of the universe. Moreover, they serve as the cradle for the development of planetary systems, including those that could host life. Through their interactions and mergers, galaxies also shape the larger structure of the universe. As galaxies collide and fuse, they release energy and spur new star formation, contributing to the dynamic and ever-evolving tapestry of the cosmos. Galaxies allow astronomers to study the history of the universe, providing a record of its expansion and the conditions that have shaped its current state. Galaxies hold the keys to unraveling the mysteries of the universe, helping us understand not just where we are, but how we got here. Dark matter and dark energy are two of the most fascinating and elusive components of our universe. Both play crucial roles in the structure and dynamics of everything we observe in the cosmos, yet they remain largely mysterious. Dark matter can be envisioned as an invisible scaffolding that shapes the universe's structure. While we can't see it directly, its presence is inferred from the gravitational effects it has on visible matter, light, and the very fabric of space itself. Observations of galaxies show that they spin at speeds that should cause them to fly apart, but they hold together tightly. This phenomenon suggests that there must be some unseen mass providing additional gravitational pull, and this is what we refer to as dark matter. It's estimated that a significant portion of the universe's total mass is hidden in this form, which interacts with ordinary matter primarily through gravitational forces. In contrast, dark energy is a mysterious force that seems to drive the acceleration of the universe's expansion. While you might think that the gravitational attraction of galactic structures would slow down cosmic expansion, observations reveal that the universe is actually stretching apart faster than before. Dark energy is thought to constitute a majority of the universe's total energy content and works against the pull of gravity. Imagine blowing up a balloon. Initially, the air fills the balloon steadily, but as you keep adding air, it begins to stretch faster and faster. In a similar way, dark energy continuously fuels the rapid expansion of the universe like a mysterious booster behind the scenes. Together, dark matter and dark energy form a critical part of the cosmic puzzle. Dark matter provides the gravitational framework for galaxies to form and cluster, while dark energy ensures that the universe continues to expand at an ever-increasing rate. Though still poorly understood, their existence challenges our understanding of physics and compels scientists to seek answers that could reshape our comprehension of the universe's past and its ultimate fate. Each discovery brings us closer to demystifying these cosmic forces, revealing a universe far more complex and intriguing than it appears at first glance. Galaxies come in various shapes and sizes, each offering a unique glimpse into the universe's intricate architecture. Among the different types, spiral galaxies are perhaps the most recognizable. They possess a stunning flat disk structure, complete with swirling arms that radiate outward. These arms are filled with stars, gas, and dust, creating vibrant regions where new stars are born. The center often features a densely packed core, usually inhabited by older stars, and often a supermassive black hole. In contrast, elliptical galaxies present a more homogeneous appearance. They resemble three-dimensional ovals or ellipses without the intricate spiral structure. These galaxies are comprised mainly of older stars, and their color tends to lean toward yellowish shades due to the lack of young blue stars. With minimal gas and dust available, the star formation rate in elliptical galaxies is relatively low. They can vary greatly in size, from smaller dwarf galaxies to giants that contain trillions of stars. Then there are irregular galaxies, which lack the defined structure seen in both spiral and elliptical types. Their form is often chaotic, accompanied by an uneven distribution of stars, gas, and dust. These galaxies typically host a wealth of young stars, giving them a unique vibrancy and luminosity. Irregular galaxies often arise from gravitational interactions with other galaxies, leading to their fragmented shapes. Each galaxy type provides vital clues about the universe's history and evolution. Their distinct characteristics illustrate the complex processes at play in the cosmos, from star formation to galactic collisions, revealing the dynamic nature of our universe. Astronomers have developed several innovative techniques to discover and study exoplanets, those planets that exist outside our solar system. The most prominent methods include the transit method and the radial velocity method. The transit method involves monitoring a star for periodic dimming. When an exoplanet passes in front of its host star from our viewpoint, it blocks a fraction of the star's light, causing a temporary dip in brightness. By measuring how much the light dims and how frequently these dips occur, scientists can infer the size of the planet and its orbital period. This technique has led to many exciting discoveries, making it one of the primary means for exoplanet detection. On the other hand, the radial velocity method looks for subtle changes in the motion of a star caused by an orbiting planet. As a planet pulls on its star due to gravitational attraction, the star shifts slightly back and forth in response. This movement affects the light emitted by the star, causing it to shift in color. Scientists can detect this shift to determine the planet's mass and orbit, allowing them to understand the system dynamics. Beyond detection, astronomers employ imaging techniques and spectroscopic analysis to study the atmospheres of exoplanets. In some cases, they can capture direct images of exoplanets using powerful telescopes that filter out the overwhelming brightness of their host stars. When astronomers observe a planet's atmosphere, they analyze the light that passes through it during a transit. By deciphering the specific wavelengths of light that are absorbed by various gases, researchers can determine the composition of the atmosphere, looking for elements that might indicate potential habitability. By deciphering the specific wavelengths of light that are absorbed by various gases, researchers can determine the composition of the atmosphere, looking for elements that might indicate potential habitability. Collectively, these methods enable astronomers to not only discover new worlds, but also paint a broader picture of their characteristics, environments, and potential for life, expanding our understanding of the universe and our place within it. A planet's habitability revolves around several key factors that create the right conditions for life as we know it. First and foremost is the presence of liquid water. This vital component is essential for all known forms of life, serving as a solvent for biochemical reactions and offering a stable environment for organisms to thrive. Temperature is another critical aspect. A planet's distance from its star influences its thermal characteristics, and being situated in the so-called habitable zone is crucial. This is the region around a star where temperatures are just right for water to exist in its liquid state, not too hot to vaporize and not too cold to freeze, creating a favorable climate for potential life. Atmospheric conditions also play a significant role. A suitable atmosphere can protect a planet's surface from harmful space radiation and maintain temperatures through the greenhouse effect. The composition of this atmosphere is equally important. An atmosphere rich in oxygen and nitrogen, for example, is conducive to supporting complex life forms, while carbon dioxide, in moderate amounts, can help regulate temperature. Additionally, geological diversity is a factor that cannot be overlooked. A planet with tectonic activity can recycle nutrients through processes that support life, contribute to a varied landscape, and foster different ecosystems. This geological dynamism can also lead to the development of a stable environment over long periods. Lastly, a planet's magnetic field acts as a shield against solar winds, protecting its atmosphere from being stripped away and ensuring stable conditions for life over geological timescales. All these factors together create a delicate balance, making planets like Earth uniquely suited for supporting life while informing our quest to find similar worlds beyond our solar system. The quest for extraterrestrial life profoundly influences how we explore exoplanets, those intriguing worlds orbiting stars beyond our solar system. Scientists are motivated by the possibility that life may exist elsewhere, propelling them to identify planets that possess the right conditions for life to thrive. This search sharpens our focus on specific characteristics of exoplanets, primarily those within the so-called habitable zone. This region around a star is neither too hot nor too cold, offering temperatures suitable for liquid water, a crucial ingredient for life as we understand it. Instruments designed to detect exoplanets now prioritize those within this zone because finding a planet with just the right conditions increases the likelihood of discovering signs of life. Moreover, research into atmospheres has become pivotal. Scientists employ advanced telescopes to analyze the light filtering through a planet's atmosphere. This analysis reveals the presence of specific gases such as oxygen and methane, which could indicate biological processes akin to those on Earth. The methodologies used in detecting these signatures guide future exploratory missions and enhance our understanding of planetary systems. The recent advancements in technology also expand our search capabilities. Missions deploying powerful space-based observatories aim to collect detailed data about distant worlds. These instruments employ techniques to monitor a star's brightness, revealing the telltale dips that occur when a planet transits in front of it. This technique allows for the estimation of a planet's size, orbit, and even potential atmosphere, irrespective of whether the planet is within our solar system. This pursuit also shapes our understanding of what life can be. Scientists are broadening their definitions based on extremophiles, organisms on Earth that thrive in harsh conditions, leading to the hypothesis that life might exist in environments previously considered inhospitable. Thus, exploring diverse exoplanets is not merely about finding Earth-like planets. It's about understanding a spectrum of potential habitats for life. Consequently, the interplay of searching for extraterrestrial life and exoplanet exploration fuels a cycle of discovery and innovation. Each new finding inspires further questions, pushing back the boundaries of our knowledge and reshaping the strategies we use to explore the universe. The excitement of possibly finding life beyond our planet not only drives scientific inquiry, but also captivates the imagination of people around the world, fostering a collective yearning to understand our place in the cosmos. The life cycle of a star begins with a massive cloud of dust and gas, primarily hydrogen, known as a nebula. Over time, gravity causes this material to collapse in on itself. As the cloud contracts, it heats up, and eventually, the core reaches a temperature sufficient for nuclear fusion to ignite. This marks the star's birth, as hydrogen atoms fuse to create helium, releasing energy that counteracts the force of gravity. Next, the star enters a stable phase called the main sequence, where it spends the majority of its life. During this time, it maintains a balance between the inward pull of gravity and the outward pressure from the energy produced in its core. The duration of this phase can vary widely. Smaller stars, like our Sun, may remain in this state for billions of years, while larger stars burn hotter and faster, exhausting their fuel in a much shorter time span. Once the hydrogen fuel in the core is depleted, the star begins to evolve. For larger stars, this can lead to the fusion of heavier elements as the core contracts and heats up, eventually forming a series of layers much like an onion. Hydrogen fuses into helium in the outer layers, while the core may undergo further fusion to create even heavier elements, such as carbon and oxygen. As the core becomes increasingly unstable, the outer layers are expelled in a tumultuous eruption known as a red giant phase. This phase is characterized by significant expansion and cooling of the outer regions, giving the star a reddish appearance. Once the core is exhausted and unable to undergo further fusion, it can no longer support the outer layers against gravitational collapse. When a massive star reaches the end of its life, it prepares for a dramatic finale, a supernova. In this explosive event, the core collapses and then rebounds violently, releasing an enormous amount of energy and material into space. This not only marks the death of the star, but also leads to the creation of elements heavier than iron, which are scattered throughout the universe. These elements can later be incorporated into new stars, planets, and even life, continuing the cosmic cycle. Thus, the life cycle of a star, from its humble beginnings in a nebula to a spectacular supernova, highlights the interconnectedness of the universe and the ever-evolving nature of celestial bodies. The evolution of a massive star is a fascinating journey that ultimately leads to the formation of a black hole. When a star has exhausted the nuclear fuel in its core, it undergoes significant changes. Initially, the core collapses under the weight of gravity as the energy produced from nuclear fusion wanes. This collapse triggers the outer layers of the star to explode in a brilliant event known as a supernova, a spectacular release of energy that can outshine entire galaxies for a brief period. During this supernova explosion, the outer layers are ejected dramatically into space, enriching the surrounding environment with elements created through nuclear fusion in the star's lifetime. What remains is the core, which has become incredibly dense. If this remaining core is heavy enough, typically several times the mass of our Sun, gravity takes over entirely. It continues to collapse inward, compressing the core to a point where the gravitational pull is so intense that nothing, not even light, can escape its grasp. At this stage, this region of space becomes what we recognize as a black hole. The boundary surrounding this point, known as the event horizon, marks where the escape velocity exceeds the speed of light. Objects and light that venture too close are trapped, making black holes invisible yet detectable through their influence on nearby stars and gas. Thus, the The life cycle of a massive star doesn't just end, it culminates in the birth of one of the universe's most enigmatic and powerful phenomena. Neutron stars are incredibly dense remnants of massive stars that have exploded in supernova events. When a star that is much larger than our Sun exhausts its nuclear fuel, it cannot support its own weight and collapses under gravity. This collapse causes protons and electrons to combine into neutrons, resulting in an incredibly small yet profoundly dense object, often just a little larger than the Sun, but packed into a sphere roughly the size of a city. The gravity on a neutron star is so strong that a small teaspoon of its material would weigh as much as an entire mountain on Earth. Pulsars are a type of neutron star that emit beams of radiation. Imagine a cosmic lighthouse. As the neutron star rotates, these beams of energy sweep across space. If the beam is directed toward Earth, we see it as pulses of light, hence the name pulsar. This rotation can be astonishingly fast, with some pulsars spinning hundreds of times per second. The radiation emitted is primarily in the form of radio waves, although it can also include visible light and X-rays. Both neutron stars and pulsars play essential roles in our understanding of the universe. They serve as natural laboratories for testing theories of physics under extreme conditions found nowhere else. The study of pulsars has also proven vital in the search for gravitational waves, subtle ripples in spacetime caused by massive cosmic events. Additionally, some pulsars are part of binary systems, where they interact with a companion star, providing insights into stellar evolution and the life cycles of stars. Neutron stars and pulsars not only exemplify the extreme conditions of the universe, but also contribute invaluable knowledge to astronomy and physics, helping us unlock the mysteries of the cosmos. Recent discoveries about black holes have dramatically expanded our understanding of these enigmatic cosmic entities. One of the most significant findings pertains to the confirmation of the existence of supermassive black holes at the centers of galaxies. Observations have shown that these colossal black holes can weigh millions to billions of times more than our Sun, influencing the formation and evolution of galaxies around them. Astronomers have also successfully captured the first direct image of a black hole located in the galaxy M87, showcasing its shadow against the backdrop of swirling gas. This groundbreaking achievement verified theories about how matter behaves in extreme gravitational fields and provided a visual confirmation of black hole existence. Another compelling discovery involves gravitational waves. The merging of two black holes generates ripples in spacetime, which have been detected by specialized observatories on Earth. These observations not only validate Einstein's theories on gravity, but also open a new avenue for exploring the universe, allowing scientists to glean insights into black hole populations and their mergers. Moreover, studies have suggested that black holes may not be entirely black. Instead, some theories propose that they might emit particles known as Hawking radiation, potentially shedding light on how black holes evaporate over time. This interplay between black holes and the particles around them leads to fascinating discussions on the balance of energy in the universe. Finally, scientists are investigating the relationship between black holes and dark matter, delving into how these mysterious forces may be intertwined. Understanding whether black holes interact with dark matter could reshape our cosmic models and clarify the fundamental makeup of our universe. These discoveries signify just the beginning, as each revelation about black holes not only tests our existing theories, but also prompts new questions, encouraging a deeper pursuit of knowledge regarding the cosmos's most mysterious objects. Observing black holes may seem impossible at first, as they do not emit light like other celestial objects. However, scientists have devised clever methods to study them using various forms of indirect evidence. One prominent technique involves monitoring the behavior of nearby stars and gas. When a black hole is surrounded by material, it forms an accretion disk, drawing in matter from its surroundings. As this matter spirals inward, it accelerates and heats up, emitting high-energy radiation, particularly in X-rays. By analyzing the light from these emissions, astronomers can infer the presence and characteristics of the black hole. Another key approach involves the gravitational effects of black holes on surrounding objects. Just like a heavy ball placed on a stretched-out sheet bends the fabric, a black hole's intense gravity affects the motion of stars and gas clouds nearby. By observing how these celestial bodies orbit around an unseen mass, scientists can calculate the black hole's mass and determine its influence in the region. Furthermore, gravitational waves, a phenomenon caused by massive objects accelerating, such as when two black holes collide, have opened a new window into studying these enigmatic entities. When these waves pass through space, they create ripples in the fabric of space-time, which can be detected by sensitive instruments on Earth. Each detection provides crucial insights into the nature of black holes and their collisions. In addition, advancements in technology, like the Event Horizon Telescope, allow scientists to capture images of the shadow a black hole casts against the brightness of its accretion disk. This innovative imaging technique provides direct visual confirmation of their existence and serves to deepen our understanding of these cosmic giants. Through these various observational techniques, scientists are piecing together the complex puzzle of black holes, uncovering their mysteries while simultaneously expanding our knowledge of the universe itself. Cosmic rays are high-energy particles from outer space that constantly bombard Earth. They mostly consist of protons, which are the positively charged particles found in atomic nuclei, but they can also include heavier atomic nuclei and even electrons. These particles travel at nearly the speed of light, carrying vast amounts of energy that can sometimes exceed what we can produce in particle accelerators here on Earth. One of the intriguing aspects of cosmic rays is their origin. While some cosmic rays come from our Sun, a significant portion appears to originate from beyond our solar system, possibly from exploding stars or active galactic nuclei, supermassive black holes at the centers of distant galaxies emitting tremendous energy. However, not all sources have been definitively identified, and this uncertainty presents a captivating mystery for scientists studying these enigmatic particles. Cosmic rays interact with Earth's atmosphere and can lead to the production of secondary particles, which can create cascading events detectable on the ground. These interactions also have implications for technology and biology, raising questions about the effects of radiation on astronauts, electronics, and even the Earth's climate. The study of cosmic rays can help scientists understand cosmic events and the fundamental nature of physics, probing deep mysteries such as the existence of dark matter or the early conditions of the universe. Each new discovery not only reveals the universe's complexity, but also hints at even greater questions yet to be answered. Astronomers have developed several ingenious methods to measure the vast distances between objects in the universe, each tailored to the scale of the distance involved. One of the earliest techniques involves using parallax, which is based on observing how much an object appears to shift against more distant backgrounds as the Earth moves around the Sun. Imagine holding a finger up and closing one eye, then switching to the other eye. Your finger shifts position relative to the background. In astronomy, this small shift helps determine the distance to nearby stars. For more distant stars, astronomers turn to a property known as luminosity. Certain types of stars, like Cepheid variables, pulsate at predictable rates. By measuring how bright they appear from Earth and knowing their true brightness, scientists can calculate how far away they are. This method relies on the relationship between brightness and distance, leveraging the known characteristics of these stars to bridge greater expanses. As astronomers venture further into the cosmos, they utilize redshift, an effect observed when objects in the universe move away from us. The light from these objects stretches, shifting toward longer wavelengths, or redder colors. By analyzing this redshift, they can infer how fast an object is moving away and estimate its distance using Hubble's law, which correlates the speed of recession to distance. For even more remote objects, such as galaxies billions of light-years away, astronomers use a combination of distance indicators and reference points, such as supernovae of a specific type, which explode with a consistent brightness. These standard candles provide a reliable measure of distances across the vastness of the universe. Each of these methods is part of a vast toolkit that astronomers employ based on the distance and context of the celestial objects they are studying. By using these diverse techniques in tandem, scientists can piece together a comprehensive picture of our universe's structure, revealing the staggering scale of cosmic distances. Our journey to comprehend the universe's size and scale has evolved dramatically from ancient times to the present day. In the early stages, thinkers believed that Earth was at the center of everything, a concept known as geocentrism. This notion placed the stars and planets within a small, finite sphere above us, leading to a limited understanding of the cosmos. As we moved into the Renaissance, figures like Copernicus shone a light on the heliocentric model, suggesting that the Earth orbits the Sun. This groundbreaking shift not only expanded our view of the solar system, but also opened a door to more profound exploration of celestial distances. The invention of the telescope in the 17th century transformed our perspective further. Astronomers like Galileo used this tool to uncover moons orbiting Jupiter and detailed the phases of Venus, providing evidence for the heliocentric system and hinting at a more extensive, complex universe. The scales involved began to become clearer in the 19th century when astronomers determined the distances to nearby stars using the method of parallax. This technique, which involves measuring the apparent shift of a star's position against distant backgrounds as Earth moves, revealed that stars are not only far away, but that many of them exist in vast numbers scattered throughout the cosmos. As we entered the 20th century, Edwin Hubble's observations revealed that galaxies are moving away from us, suggesting our universe is expanding. This idea meant that the universe is even more enormous than we could have imagined, encompassing billions of galaxies spaced apart across unfathomable distances. Today, with the advent of advanced telescopes and spacecraft, we have mapped out the observable universe, giving us a sense of its size that is mind-boggling. Counting billions of light-years between galaxies helps us understand that what we see is just a fraction of the entire universe. Dark matter and dark energy now challenge our understanding, as these components appear to make up a significant portion of the universe's mass and energy, but remain largely mysterious. Our grasp of the universe's scale has transitioned from a small, enclosed cosmos to an expansive, dynamic entity containing realms full of galaxies, each with countless stars. Each discovery adds layers to our understanding, pushing the boundaries of what we know and continually igniting curiosity about the vast unknown that lies beyond. Edwin Hubble played a pivotal role in transforming our understanding of the universe at the beginning of the 20th century. Before his groundbreaking work, many believed the Milky Way galaxy encompassed the entirety of the cosmos. The prevailing thought limited our understanding of what lay beyond our own stellar neighborhood. Hubble challenged this narrow view through his observations of distant galaxies, revealing that these were, in fact, separate systems entirely, far beyond the boundaries of our galaxy. In the 1920s, by using powerful telescopes, Hubble studied the light from these galaxies and discovered that most of them were moving away from us. This was significant because it suggested that the universe is expanding, a concept that contradicted the static model that many scientists adhered to at the time. Hubble's observations led to the formulation of Hubble's law, which quantified the relationship between the distance of galaxies and their speed. Essentially, the farther a galaxy is from us, the faster it appears to be receding. This discovery opened new avenues for understanding cosmic origins. Hubble's work influenced the development of the Big Bang theory, providing a scientific framework for the beginning of the universe and suggesting it has evolved over time from a hot, dense state. He also contributed to the realization that the universe is vast and dynamic, reshaping not just the scientific community's approach to cosmology, but also the general public's perception of humankind's place in the cosmos. The implications of Hubble's findings continue to resonate, illustrating that our universe is not fixed, but continually changing. A grand tapestry of galaxies, stars, and cosmic events expanding before our eyes. The concepts of space-time and relativity fundamentally reshape our comprehension of the universe. Traditionally, we viewed space and time as separate entities, much like distinct tracks of a train. However, Albert Einstein's theory of relativity fused these two ideas into a single framework known as space-time. This interaction means that space can be warped by the presence of mass, and time can flow differently based on speed and gravitational forces. Imagine a large object, like a planet, resting on a trampoline. The fabric of the trampoline represents the fabric of space-time. As the planet sinks into the trampoline, it creates a curve, affecting the way smaller objects move around it. Similarly, in our universe, massive bodies like stars and galaxies create curves in space-time, influencing the paths of other objects as they travel nearby. This effect not only explains the orbits of planets, but also governs the behavior of light when it passes close to massive objects, bending its path in a phenomenon known as gravitational lensing. Moreover, relativity introduces a mind-bending alteration in our perception of time. As you move faster, approaching the speed of light, time begins to slow down for you compared to someone who remains stationary. This leads to fascinating scenarios where astronauts traveling at high speeds in space would age more slowly than people on Earth. This thought experiment illustrates how our understanding of causality, what happens first and what takes longer, becomes intertwined with the structure of space-time. Because space-time is a dynamic entity, it requires us to rethink concepts like distance and duration. Events that appear simultaneous from one perspective could unfold at different times from another. This interconnectedness of time and space prompts profound questions about the nature of reality itself and challenges our notions of past, present, and future. Overall, understanding space-time and relativity opens the door to deeper insights into the workings of the cosmos, revealing a universe that is more interconnected, dynamic, and complex than previously imagined. Gravitational waves are ripples in the fabric of space-time produced by some of the universe's most violent events, such as the collision of black holes or the merging of neutron stars. Their existence was first predicted over a century ago by Albert Einstein, when he formulated the theory of general relativity. However, they remained elusive until the story took a thrilling turn in the 21st century. The groundbreaking evidence for gravitational waves emerged in 2015 when the LIGO detector, an observatory designed specifically to sense these faint distortions, registered an event described as a black hole merger. This detection marked a monumental moment in astrophysics. LIGO operates by using laser beams to measure incredibly small changes in distance caused by passing gravitational waves. When a wave reaches Earth, it alters the space between the detector's mirrors ever so slightly, allowing scientists to observe the faint signals. Following this initial detection, multiple events have been recorded, each adding to the growing body of evidence. One remarkable incident, occurring in 2017, included the combined detection of gravitational waves and electromagnetic signals from the merger of neutron stars. This event not only demonstrated that gravitational waves could provide new insights into cosmic phenomena, but also set the stage for what is known as multi-messenger astronomy, where researchers can study the universe using different types of signals, from gravitational waves to light. Through careful analysis and advanced technology, the scientific community has built a robust framework of evidence supporting the existence of gravitational waves. These discoveries not only validate Einstein's predictions, but also open new avenues for understanding the universe, offering a fresh lens through which to view phenomena that were once beyond our reach. Time dilation and gravitational lensing are two fascinating phenomena that reveal the complexities of our universe, each showcasing how gravity influences space and time. Time dilation occurs due to the effects of gravity or speed. When an object falls into a strong gravitational field, such as that created by a massive star or black hole, time for that object slows down relative to someone far away from that gravity's grasp. This effect can be imagined as a race between two clocks, one in a low-gravity environment and another deep in a gravitational well. The clock in the stronger gravitational field ticks more slowly, illustrating how gravity has the power to warp time. This phenomenon underlines one of the fundamental concepts of Einstein's theory of relativity, where the fabric of space-time is not a static backdrop, but rather a dynamic entity influenced by mass. Gravitational lensing, on the other hand, occurs when the light from a distant star or galaxy bends around a massive object, like a galaxy cluster, due to gravity's influence. Envision this process as the way a curved glass lens affects the light passing through it. Scientists are currently engaged in a multitude of ambitious projects to unravel the mysteries of dark matter and dark energy, two of the most enigmatic components of our universe. Despite making up about 95% of the cosmos, their nature remains largely unknown. To investigate dark matter, researchers are designing and constructing sensitive detectors placed deep underground. These locations shield the detectors from cosmic rays and other background interference. The goal is to capture hypothetical particles called WIMPs, or weakly interacting massive particles, which are thought to account for dark matter's existence. Experiments like these aim to observe potential interactions or collisions with regular matter, although no conclusive detections have yet been reported. In addition, astronomers utilize large telescopes to study the gravitational effects of dark matter on visible matter. By examining the way galaxies rotate and how light bends around massive clusters, an effect known as gravitational lensing, they can map out dark matter's distribution. Such studies offer indirect evidence since dark matter does not emit light or energy, making it invisible to conventional observation methods. On the front of dark energy, which is driving the accelerated expansion of the universe, researchers are employing wide-field surveys. These investigations involve taking detailed photographs of the night sky, documenting the light from millions of galaxies over extensive areas. By analyzing the redshift of these galaxies, the shift in light towards the red end of the spectrum due to their movement away from us, scientists can determine the rate of expansion and gauge how it changes over time. Another innovative method is through the study of supernovae, particularly those of a certain type known as type Ia. These stellar explosions serve as standard candles because their brightness remains consistently uniform. By measuring the distance to these supernovae and comparing it to their redshift, scientists can deduce information about the rate of cosmic expansion. Projects like the Euclid spacecraft and the James Webb Space Telescope are expected to further illuminate these mysteries. They will gather unprecedented data on the structure and evolution of the universe, providing insights that may lead to a deeper understanding of both dark matter and dark energy. As these efforts progress, the scientific community remains hopeful that these endeavors will not only shed light on what constitutes the majority of our universe, but might also unveil new physics beyond our current understanding. In the vastness of space, unseen forces play a crucial role in shaping the evolution of the universe. One of the most significant of these influences is gravity, which pulls objects together, forming galaxies, stars, and eventually planets. Imagine the universe as a massive cosmic web where each node represents a galaxy, and the strands are the gravitational forces binding them. Over immense timescales, gravity causes clusters of matter to coalesce, leading to the spectacular formations we observe today. However, gravity is not the only force at play. Dark energy, a mysterious, repulsive force, exerts its influence by driving the expansion of the universe. Picture this as the fabric of space itself stretching, making galaxies drift apart over time, like dots on a balloon inflating. This phenomenon was unexpected. Scientists once believed that gravity would slow down the expansion, but the discovery of dark energy revealed that the universe is not only expanding, but that this expansion is accelerating. These forces interact in intricate ways. As galaxies merge or collide due to gravitational attraction, they trigger star formations and other cosmic events. leading to the birth of new elements and more complex structures. On a larger scale, the interplay between dark energy and gravity will ultimately dictate the universe's fate. Will it continue to expand indefinitely, growing colder and emptier, or will gravity eventually dominate, pulling everything back together in a grand cosmic collapse? Thus, these unseen forces, gravity and dark energy, are fundamental in steering the universe's journey, dictating everything from the formation of galaxies to the ultimate destiny of the cosmos. Understanding their effects not only reveals the structure of the universe, but also deepens our appreciation for the delicate balance of forces that governs all existence. Current technologies are revolutionizing our understanding of the universe's dark components, which include dark matter and dark energy. Imagine these mysterious entities as the unseen fabric of the cosmos, shaping its structure yet remaining elusive. One major advancement comes from powerful telescopes equipped with cutting-edge sensors. These instruments allow astronomers to capture light from distant galaxies and cosmic events, revealing how these entities influence the movement of visible matter. For example, the way galaxies rotate and cluster suggests the presence of a substantial amount of unseen mass. This indirect evidence points toward dark matter, as it provides the necessary gravitational pull to maintain these formations. Moreover, satellite missions, like those observing cosmic microwave background radiation, have enhanced our grasp of dark energy. This ancient light carries information from a time when the universe was much younger. By analyzing slight temperature fluctuations in this radiation, scientists can infer how dark energy drives the acceleration of the universe's expansion. In addition, advancements in computer simulations play a vital role. These simulations recreate cosmic structures and the behavior of dark components under various conditions. By comparing these simulations with actual observations, researchers can refine their models and better understand how dark matter and dark energy interact with regular matter. Finally, the development of particle detectors on Earth aims to observe potential dark matter particles directly. These detectors are placed deep underground to shield them from cosmic noise, creating a controlled environment to capture rare interactions that might reveal the nature of dark matter. Through this combination of sophisticated observational techniques, powerful simulations, and innovative experimental approaches, our knowledge of these enigmatic components continues to expand, painting a clearer picture of the universe's hidden dynamics. The evidence for the accelerating expansion of the universe centers primarily around observations of distant supernovae and the cosmic microwave background radiation. In the late 20th century, astronomers observed certain types of supernovae, specifically those known as Type 1a, which explode in a consistent manner. By measuring the brightness of these supernovae from various distances, scientists were surprised to find that the more distant explosions appeared dimmer than expected. This dimming indicated that these supernovae were farther away than the models predicted, suggesting that something was causing the universe to stretch faster than previously thought. The light from these supernovae takes billions of years to reach us. Therefore, they serve as time machines, revealing information about the conditions of the universe long ago. Additionally, observations of the cosmic microwave background radiation, the afterglow of the Big Bang, provide a snapshot of the early universe. These measurements show uniform temperature fluctuations, suggesting that the universe has been expanding and cooling over time. The patterns found in this radiation align with the idea of an expanding universe, but new models incorporating dark energy, the mysterious force driving the acceleration, fit the data even better. Together, these pieces of evidence paint a picture where the universe is not just expanding, but doing so at an ever-increasing rate, hinting at forces that continue to shape its destiny in ways we are only beginning to understand. As we look to the future, the expanding universe holds a treasure trove of discoveries waiting to be uncovered. Scientists anticipate that by studying distant galaxies, we will gain insights into the conditions and fundamental forces that governed the early universe. Imagine peering back in time. By observing light from galaxies billions of years old, we can piece together how the cosmos evolved from a hot, dense state into the vast expanse we see today. One intriguing avenue of exploration lies in the understanding of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. If we can decipher its nature, we may unlock secrets about the universe's ultimate fate. Will it continue to expand forever, or could it one day collapse back in on itself? Each revelation on dark energy not only reshapes our cosmic timeline, but also enhances our understanding of the fabric of space itself. Additionally, the discoveries of new exoplanets, worlds beyond our own, could redefine the search for life. As technology advances, we will be able to examine the atmospheres of these distant planets. Identifying potential biosignatures could profoundly impact our understanding of life's possibilities in the universe, challenging us to reconsider what it means to be alive. Another exciting prospect is the potential detection of gravitational waves from catastrophic cosmic events like merging black holes or neutron stars. These ripples in spacetime carry information about phenomena that have been invisible to traditional telescopes, offering new tools to study the universe's most enigmatic occurrences. As we continue our journey into the cosmos, the expanding universe has countless stories to tell, riddled with surprises that could change our understanding of reality. Each discovery not only fuels scientific curiosity, but also deepens our connection to the vast and mysterious universe we inhabit. Advancements in telescope technology have significantly enhanced our understanding of the universe's expansion. Modern telescopes are equipped with powerful imaging capabilities and sophisticated sensors that allow us to observe distant galaxies, revealing how far away they are and how fast they are moving. This is vital because evidence of expansion is mostly gathered by examining the light emitted from these galaxies. One of the key ways telescopes contribute to this exploration is through the observation of redshift. As galaxies move away from us, the light they emit stretches, shifting towards the red end of the spectrum. Highly sensitive telescopes can detect these subtle changes in light. By measuring the amount of redshift, astronomers can determine the speed at which a galaxy is receding. The more distant a galaxy is, the faster it appears to be moving away, supporting the notion that the universe is expanding. Additionally, advancements have improved our ability to observe not only visible light, but also other wavelengths, such as infrared and ultraviolet. This broader spectrum of light gives scientists a more complete view of cosmic phenomena. For instance, observing light from early galaxies helps astronomers trace the history of expansion over time, providing insights into how the universe has evolved since its inception. Moreover, new technologies in telescope design, such as adaptive optics, allow for clearer images by compensating for atmospheric distortions. This clarity is essential for detailed studies of celestial bodies, revealing structures and formations that might otherwise remain hidden. By taking precise and high-resolution images, researchers can analyze the distribution of galaxies and their movements within the universe more accurately. Enhancements in telescope technology have not only improved our observational capabilities, but also deepened our understanding of the cosmos. They enable scientists to gather critical data about the expansion of the universe, confirming that it is not just a static entity, but one that has been expanding since its beginning and continues to do so today. Each advancement brings us closer to piecing together the history and fate of the universe itself. Gravity is the invisible force that governs the cosmos, shaping the formation and movement of celestial bodies from the tiniest particles to sprawling galaxies. At its core, gravity pulls objects toward one another based on their mass. When a large body, like a star or a planet, forms from a cloud of gas and dust in space, gravity causes the material to clump together. As more mass accumulates, the gravitational pull strengthens, attracting even more surrounding matter. This process can lead to the birth of a new star, which can eventually ignite nuclear fusion and light up the cosmos. Once celestial bodies form, gravity continues to dictate their movements. For instance, a planet in orbit around a star is held in its path not just by its initial momentum, but by the star's gravitational pull. Imagine swinging a ball on a string. As you move your arm, the ball travels in a circular path due to the tension pulling it inward. In a similar manner, planets revolve around stars, and moons follow planets, maintaining a delicate balance between their inertia and the gravitational forces acting on them. Gravity also plays a pivotal role in phenomena such as tides, where the gravitational pull of the moon and the sun affects Earth's oceans. Moreover, this force contributes to the dynamics within galaxies, where stars orbit the galactic center due to immense gravitational attraction. In regions where gravity is exceptionally strong, like near black holes, the effects can be dramatic, bending light and warping space-time itself. Thus, gravity is a fundamental player in the ongoing dance of celestial bodies, influencing their formation, movement, and ultimate fate in the grand tapestry of the universe. Gravitational waves are ripples in the fabric of space and time caused by some of the most violent and energetic processes in the universe, such as the collision of massive black holes or neutron stars. Picture throwing a stone into a calm pond. The waves propagate outward, distorting the surface. Similarly, when two dense objects accelerate in space, they create disturbances that spread across the universe at the speed of light. Detecting gravitational waves offers a new way to observe cosmic events that are otherwise invisible. Traditional astronomy relies on electromagnetic waves, like light, to study celestial phenomena. However, many significant cosmic events, like black hole mergers, emit little to no light. Gravitational waves provide us with a different perspective, allowing scientists to hear the universe's most dramatic moments. By analyzing these waves, researchers can extract vital information about the properties of the objects involved, including their masses and the dynamics of their interactions. This data enhances our understanding of the life cycles of stars and the formation of black holes, shedding light on the processes that shape our universe. Moreover, it opens the door to a deeper exploration of fundamental physics, including the nature of gravity itself and the possibility of uncovering new forces or phenomena yet to be understood. Gravitational waves are not just a method of observation. They act as cosmic messengers, telling us stories about the universe that light alone could never reveal. Albert Einstein's theories brought a revolutionary shift in how we understand gravity, particularly with his general theory of relativity. Traditionally, gravity was seen as a force acting at a distance, pulling objects towards one another, as described by Isaac Newton. However, Einstein introduced a different perspective. Gravity is not simply a force, but a warp in the fabric of space and time itself. Imagine space and time as a vast, flexible sheet. When a massive object, like a planet or a star, sits on this sheet, it creates a dip or curve around it. Any smaller object moving close to that weighty body will follow the curve created by this deformation. So rather than being drawn by an invisible force, these smaller objects are actually following the natural contours of space-time. This understanding clarifies why planets orbit stars in predictable paths and why light bends in the presence of massive objects, what we call gravitational lensing. This bending of light has been observed when light from distant stars passes near massive galaxies. Such phenomena hadn't been easily explained under the old Newtonian framework. Einstein's views also influence how we perceive gravity's effect on time. Near massive bodies, time appears to flow more slowly than it does far away from such masses. This means that an observer close to a significant gravitational mass would experience time differently than someone far away from it. As a result, our cosmic perspective of time and space has expanded, proving that these are deeply interconnected dimensions, intricately shaped by the presence of mass. In sum, Einstein did not merely provide a new equation, but transformed gravity into an essential aspect of a unified reality, a realm where space and time flow together in a dance governed by the mass of objects, influencing everything from the trajectory of planets to the very nature of time itself. The quest to discover extraterrestrial life is filled with both formidable challenges and groundbreaking advancements. One of the primary challenges is the vastness of outer space itself. The universe is immense, and searching for life means sifting through billions of stars in billions of galaxies, which makes it incredibly difficult to narrow down where to look. Another significant hurdle is the limitations of our technology. Current instruments are designed to detect signature signs of life, such as specific gases in a planet's atmosphere. However, these measurements can be intricate and susceptible to misinterpretation. Moreover, many planets are located light years away, making direct observation a steep undertaking. This distance implies that we have to rely heavily on indirect methods and sophisticated models to infer if a planet might harbor life. The search also faces the challenge of defining what life actually is, especially in forms not found on Earth. Most studies focus on what we know, carbon-based life forms that depend on water. But imagine life that could exist in entirely different conditions, using different elements or processes. This expands our search parameters, but also complicates it, as we may overlook potential forms of life simply because they don't match our Earth-centric expectations. On the other hand, significant breakthroughs have emerged alongside these challenges. Advancements in telescope technology, for example, have enabled scientists to analyze the atmospheres of exoplanets, which are planets orbiting stars outside our solar system. By observing the light passing through these atmospheres, researchers can identify chemical signatures that might indicate the presence of life-sustaining conditions, such as oxygen, methane, or water vapor. The discovery of extremophiles, organisms that thrive in Earth's harsh environments, has also transformed our understanding of where life might exist. From the icy depths of oceans to the scalding hot springs, these resilient forms of life suggest that we should broaden our search to include environments thought to be inhospitable, such as the subsurface oceans of icy moons like Europa or the clouds of Venus. Projects like the Mars rover missions have made tangible strides in exploring potential biosignatures on other planets. With each successful mission, we gather more data, creating a clearer picture of our neighboring worlds. Simultaneously, the emergence of collaborative efforts within the scientific community has amplified our ability to share findings and strategies, thus accelerating the pace of discovery. Ultimately, the journey to uncover extraterrestrial life is a blend of rigorous scientific inquiry and a hint of adventure, as we embrace the unknown and push the boundaries of what we consider possible. Each setback serves as a stepping stone, and every breakthrough offers new hope in our pursuit of understanding our place in the cosmos. Scientists employ a meticulous process to interpret signals from space as potential signs of life. At the heart of this endeavor lies the understanding of what constitutes a signal. When researchers detect unusual patterns or frequencies emanating from distant worlds, they first establish whether these signals are natural or artificial. This involves examining the characteristics of the signals. Are they regular, rhythmic, or random? Certain features, such as repeated intervals, may suggest a systematic source, which could indicate intelligent communication. To decode these signals, scientists analyze their frequency and modulation. For instance, radio waves transmitted from extraterrestrial sources are carefully scrutinized for specific patterns that might bear resemblance to human-made communication. The search for life often relies on the presence of unique elements, such as the signature spectral lines of certain gases that might indicate biological activity. Educated predictions can be made based on the conditions necessary for life, like water, organic compounds, and energy sources. Furthermore, each discovery is compared against a database of known signals to differentiate between expected cosmic phenomena, such as pulsars or quasars, and potential indicators of intelligent origin. This comparative analysis forms the basis for hypotheses on extraterrestrial life. Scientists remain highly cautious in their interpretations, emphasizing the need for supporting evidence. When a signal is deemed worthy of further investigation, interdisciplinary teams of astronomers, biologists, and data scientists collaborate to design thorough observational strategies, continuously questioning and testing their hypotheses. Ultimately, the search for signals as signs of life is a thrilling blend of observation, analysis, and imagination, driven by the enduring question of whether we are alone in the universe. The search for alien life in our galaxy leads us to some intriguing regions, each offering unique conditions that may support extraterrestrial beings. One of the most exciting areas is the so-called Goldilocks zone. This zone refers to the habitable zones around stars where temperatures are just right, not too hot and not too cold, allowing for liquid water to exist. Since water is a fundamental building block of life as we understand it, stars with planets within this zone are prime candidates. Moreover, specific types of stars known as M-dwarfs or red dwarf stars are particularly appealing. These stars have long lifespans, potentially granting their planets ample time for life to evolve. Additionally, many of these stars are known to host multiple planets, increasing the chances of finding habitable environments. Another exciting region is around the large gas giants of our galaxy, specifically their moons. For instance, moons like Europa and Enceladus in our own solar system show intriguing signs of subsurface oceans beneath thick layers of ice, suggesting they may harbor life. The potential for similar conditions in the atmospheres of exoplanets, planets orbiting other stars, also can't be overlooked. Some have been found in atmospheres rich in the chemical elements we associate with life, such as oxygen and methane. Finally, areas where stellar conditions allow for complex organic molecules to form, like regions of ongoing star formation, could be hotspots for the building blocks of life. These areas, rich in dust and gas, hold potential for the synthesis of life's essential components. All these locations combined create a tapestry of possibilities, each awaiting exploration and discovery in our quest to find life beyond Earth. Throughout history, brilliant scientists have unraveled the mysteries of the universe, each contributing unique insights and groundbreaking discoveries. One of the earliest figures to shape our understanding was Galileo Galilei. With his use of the telescope, he challenged traditional views of the cosmos, revealing celestial bodies that had never before been seen. He discovered mountains and craters on the moons of Jupiter, and the phases of Venus, setting the stage for modern astronomy. Another pivotal scientist is Sir Isaac Newton. His formulation of the laws of motion and universal gravitation provided a framework for understanding how objects interact in the cosmos. By describing how gravity operates on both earthly and heavenly bodies, Newton laid the groundwork for classical mechanics. Moving into the 20th century, Albert Einstein revolutionized our perception of time and space with his theory of relativity. He introduced the idea that gravity is not merely a force, but a curvature in the fabric of space-time caused by mass. This radical shift fundamentally changed how we understand the universe's structure and dynamics. Equally significant was Edwin Hubble, who expanded our understanding of the universe's scale. Through his observations, he demonstrated that the universe is not static but expanding, leading to the formulation of what we now call the Big Bang Theory. His discovery of distant galaxies and their redshifts provided compelling evidence for this dynamic universe. More recently, scientists like Stephen Hawking have deepened our comprehension of black holes and the nature of time. By melding quantum mechanics with general relativity, his work opened new avenues of exploration into the universe's most enigmatic phenomena. These scientists, among many others, have collectively constructed an evolving narrative of the cosmos, each adding crucial pieces to the puzzle of our existence and the vastness of the universe around us. Technological advancements have been the backbone of our achievements in space exploration, propelling us further into the cosmos than ever before. At the core of this revolution is the evolution of rocketry. Early rockets struggled to escape Earth's gravitational pull, but breakthroughs in materials science and propulsion technology have created powerful engines capable of carrying massive payloads into space. With the introduction of reusable rocket systems, the cost of accessing space has significantly decreased, enabling more frequent and ambitious missions. Instrumentation also plays a critical role in our exploration efforts. The development of sophisticated telescopes and sensors has enhanced our ability to observe distant celestial bodies, revealing hidden details about galaxies, planets, and even potential exoplanets with conditions that may support life. These instruments gather a wealth of data, allowing scientists to simulate conditions that exist far beyond our reach. Communication technologies have also transformed space exploration. The advent of high-frequency communication allows spacecraft to send data back to Earth in real time, facilitating immediate analysis of findings. This swift exchange of information is crucial for mission success, enabling scientists to make timely adjustments and informed decisions based on real-time data. Furthermore, advancements in artificial intelligence and robotics have begun to play an essential role in space missions. Autonomous rovers and spacecraft can carry out complex operations without needing constant oversight from mission control, exploring environments that are too hazardous for humans. These robots can analyze samples, take measurements, and even make decisions on the fly, greatly expanding our capacity to investigate other worlds. As we look toward the future, technologies such as 3D printing and advanced life support systems promise to enable longer missions, even to distant destinations like Mars. With each innovation, we not only push the boundaries of what's possible in space exploration, but also deepen our understanding of the universe and our place within it. Each technological leap aids in answering fundamental questions about life beyond Earth and the nature of the cosmos itself, making every mission a step toward greater discoveries. Interdisciplinary collaboration has been a cornerstone of cosmic research, significantly enhancing our understanding of the universe. When scientists from diverse fields come together, they bring unique perspectives and expertise that can transform a single idea into a groundbreaking discovery. For instance, astronomers who study celestial bodies may team up with physicists to investigate the fundamental forces that govern the universe. This collaboration allows for a richer analysis of phenomena like supernova or black holes, linking observational data with theoretical frameworks. One prime example is the collaboration during the observation of gravitational waves. This endeavor required not only physicists, but also engineers, computer scientists, and even data analysts to design the necessary equipment, interpret the signals, and share findings across various platforms. Their joint efforts led to a new way of observing the cosmos, illustrating how interconnected disciplines can yield monumental advancements. Moreover, these partnerships often lead to the development of innovative technologies and methodologies. Techniques from fields like biology or materials science can be applied to improve instruments used in space exploration, resulting in more sensitive and accurate measurements. Each discipline informs the other, creating a synergy that allows cosmic research to flourish. The communication of findings across disciplines also enriches public engagement and education. When scientists work together, they can convey complex ideas in more accessible ways, sparking interest in diverse audiences. In turn, this broadens the support for space exploration and research, reinforcing the idea that understanding our universe is a shared human endeavor, transcending the boundaries of individual sciences. By fostering an environment where knowledge and expertise flow freely, interdisciplinary collaboration continues to propel cosmic research to new heights. The cosmic microwave background, or CMB, is a faint glow that fills the universe and serves as a remnant of the early stages of our cosmos. Imagine the universe as a primordial soup of particles and energy, approximately 300,000 years after the Big Bang. At that juncture, the universe had cooled enough for protons and electrons to combine and form hydrogen atoms, allowing light to travel freely. This light, which was emitted as the universe transitioned from opaque to transparent, has stretched and cooled over billions of years into microwave radiation. Think of the CMB as the afterglow of the Big Bang, offering a snapshot of the universe when it first became transparent. Its existence provides critical evidence for the Big Bang theory, as it confirms that the universe had a hot, dense beginning. The slight variations in temperature within the CMB are crucial, as these fluctuations represent the early density differences that ultimately led to the formation of galaxies and large-scale structures we see today. Additionally, the CMB allows cosmologists to glean details about the universe's composition, age, and its expansion rate. By analyzing its properties, scientists can make inferences about the universe's development over time, including the influence of dark matter and dark energy. The cosmic microwave background serves as a cosmic map, guiding researchers through the evolution of the universe and deepening our understanding of its very nature. The journey to discovering the cosmic microwave background began in the mid-20th century. Scientists were investigating radio waves and their origins when they stumbled upon an unexpected phenomenon. In the early 1960s, Arno Penzias and Robert Wilson were working with a highly sensitive radio telescope in New Jersey. They faced a puzzling problem. No matter where they pointed their instrument, it picked up a persistent, faint signal that seemed to come from everywhere in the sky. Initially, Penzias and Wilson considered various explanations, such as interference from nearby sources or even a pigeon nesting within their telescope. However, their thorough investigations ruled out these possibilities. Meanwhile, across the country, a group of researchers led by George Gamow and others was theorizing about the Big Bang and the remnants of that explosive event. They predicted that an afterglow from the early universe should still be detectable in the form of microwave radiation. When Penzias and Wilson learned about this theory, everything fell into place. They had effectively discovered the cosmic microwave background radiation, a faint glow that permeates the universe and serves as a relic from the time when the universe was a hot, dense state, just a fraction of a second after the Big Bang. This radiation, cooled through the eons, now exists at a temperature just above absolute zero. The significance of the cosmic microwave background cannot be overstated. It provides crucial evidence for the Big Bang theory, supporting the idea that the universe has expanded and cooled over billions of years. By studying this background radiation, scientists can glean information about the early universe's conditions, including its density, temperature, and the distribution of matter. Moreover, the tiny variations in temperature of this radiation tell us about the early seeds of structure that would eventually grow into galaxies and clusters of galaxies. The cosmic microwave background acts as a snapshot of the universe during its infancy, unlocking secrets that help us understand the cosmos today. Cosmic background radiation serves as a crucial piece of evidence for understanding the early universe. Imagine it as a faint afterglow left over from the moment the cosmos began, specifically from a period known as the Big Bang. This radiation fills the universe uniformly, like a gentle warmth that lingers long after a fire has gone out. When astronomers observe this background radiation, they are essentially peering back in time, discovering conditions that existed just a few minutes after the birth of the universe. The significance of this radiation lies in its uniformity and slight variations. These subtle fluctuations in temperature indicate regions of denser matter and those with less, which ultimately led to the formation of galaxies and large-scale structures we see today. By studying these variations in detail, scientists can glean insights about the universe's early composition, including the types of particles present and their distributions. Moreover, analyzing cosmic background radiation aids in refining our understanding of fundamental cosmological concepts, such as the rate of expansion of the universe. This is important because it helps scientists estimate the age of the universe itself and the dynamics that have influenced its growth over billions of years. Cosmic background radiation acts like a celestial photograph that captures an infancy of the universe, unlocking secrets that shape our knowledge of how everything came to be. Telescopes and satellites have revolutionized our exploration of the universe, acting as our eyes to the cosmos in ways that terrestrial observation simply cannot match. Imagine trying to see a distant ship on the horizon with the naked eye. Now, think of the clarity a powerful telescope offers, bringing that ship into sharp focus. Telescopes, especially those placed beyond our atmosphere, eliminate the distortions caused by Earth's atmosphere, granting us crisp, detailed views of celestial objects. Through these advanced instruments, we have gained crucial insights into the nature of space. Telescopes can capture different wavelengths of light, from infrared to ultraviolet, revealing hidden aspects of cosmic phenomena. This capability allows us to study everything from star formation in vast galactic nurseries to the remnants of explosive supernovae. Each wavelength tells a different story about the energy and chemistry of the universe, leading to discoveries we could only dream of before. Satellites add another layer to this exploration. They orbit the Earth or travel to other celestial bodies, gathering data without the interference of atmospheric conditions. Observatories like the Hubble Space Telescope have provided images that demonstrate the breathtaking beauty of our universe while also deepening our understanding of its structure and evolution. These instruments can measure the faint light from distant stars, analyze the atmospheres of exoplanets, and even track cosmic events as they unfold. Furthermore, advancements in technology have made these devices increasingly accessible. The combination of smaller, more efficient satellites and ground-based observatories has democratized our understanding of the universe. Scientists and enthusiasts alike can now analyze data that was once limited to a select few, creating a collaborative environment that accelerates discovery. Telescopes and satellites have not only improved our observational capabilities, but have also expanded our comprehension of fundamental questions about existence and the nature of the cosmos. They continuously peel back the layers of mystery surrounding our universe, revealing both its grandeur and complexity. Computer simulations are essential tools for understanding the vast and complex behaviors of cosmic phenomena. These simulations allow scientists to recreate the conditions of the universe, from the formation of galaxies to the intricate dynamics of black holes, in a virtual environment. By simulating these processes, researchers can explore scenarios that would be impossible to observe directly. At the heart of these simulations is the use of mathematical models that describe physical laws, such as gravity and thermodynamics. Computer programs take these laws and apply them to large scales, forming a digital universe where scientists can manipulate variables like mass, velocity, and temperature. This enables the examination of how different forces interact over time, providing insights into events such as the birth of stars or the collision of galaxies. By running these simulations, scientists can predict outcomes and test their theories against the data we gather from telescopes and satellites. For instance, if a simulation shows how a galaxy might evolve over billions of years, researchers can then look for specific signatures in real observations to validate their models. Furthermore, these simulations can uncover unexpected phenomena, suggesting new areas for research or even leading to breakthroughs in our understanding of the universe. Ultimately, computer simulations bridge the gap between theoretical predictions and empirical observations, revealing the dynamic and often chaotic nature of cosmic events. They serve as a laboratory for the universe, where ideas can be explored and refined, driving our quest for knowledge about the cosmos. Big data is revolutionizing our understanding of the universe in profound ways. The cosmos is an intricate tapestry woven from countless variables: stars, galaxies, black holes, and chemical compositions. With the advent of technology, we can now collect vast amounts of data from telescopes and satellites that observe our universe in different wavelengths, including visible light, infrared, and radio waves. Consider the multitude of galaxies, each containing billions of stars. Traditional methods of analysis simply cannot process this staggering volume of information. Enter big data. By employing powerful algorithms and sophisticated computational techniques, scientists can sort through enormous datasets to identify patterns and correlations that would be impossible for humans to discern alone. For instance, in studies of galaxy formation, researchers use data on structure and distribution to model how these vast entities evolve over time. By analyzing the light emitted from distant galaxies, scientists can infer not just their current state, but their history, revealing how they interacted with surrounding cosmic material over billions of years. This process often involves utilizing advanced machine learning techniques, which allows computers to learn from the data, improving their ability to predict and classify cosmic phenomena. Moreover, when observing events like gravitational waves or the collision of neutron stars, big data enables the merging of signals from multiple detectors spread across the globe. The combination of these signals can enhance our understanding of such events, shifting our comprehension of fundamental physics and the extreme conditions present in our universe. Big data acts as a cosmic lens, providing insights into the otherwise hidden intricacies of the universe. It not only allows us to manage the vastness of information available, but it also opens new frontiers for exploration, enabling scientists to unravel the mysteries of the cosmos with greater precision than ever before. Several upcoming space missions have the potential to transform our understanding of the universe, promising to uncover new insights and deepen our knowledge across various fields of astronomy and astrophysics. One of the most anticipated missions is the James Webb Space Telescope, designed to observe the cosmos in infrared light. This telescope will allow scientists to peer into the early universe, revealing the formation of stars and galaxies that occurred just after the Big Bang. By gathering light from very distant celestial objects, it will provide clarity on the life cycle of stars and the atmospheres of exoplanets, possibly identifying conditions suitable for life. Another exciting mission is the European Space Agency's Euclid spacecraft, which aims to investigate dark energy and dark matter. By mapping the geometry of the universe with great precision, Euclid will collect data that can help scientists understand the role of these mysterious components in cosmic expansion and structure formation. This knowledge could lead to groundbreaking developments in our comprehension of the fundamental forces that govern the universe. NASA's Artemis program, set to return humans to the Moon, will not only facilitate lunar exploration, but will also serve as a stepping stone for future missions to Mars. The data and experience gained from Artemis will enhance our understanding of the lunar environment, which may provide clues about the solar system's history and prepare future generations for deeper space exploration. Finally, the Mars Sample Return Mission, a collaborative effort between NASA and the European Space Agency, aims to bring samples of Martian soil back to Earth. This could answer long-standing questions about past life on Mars and the planet's geological history, offering direct evidence that could redefine our concept of habitability beyond Earth. Together, these missions represent a pivotal moment in space exploration, each contributing unique pieces to the vast puzzle of the universe and potentially reshaping our fundamental understanding of existence itself. International collaborations are transforming the landscape of space exploration, allowing countries to pool their resources, expertise, and technology. Imagine the vastness of outer space, where the challenges of exploration are immense and complex. No single nation has all the answers or capabilities to tackle these challenges alone. By coming together, countries can share their unique strengths, leading to faster advancements and richer scientific discoveries. For instance, numerous nations have partnered through initiatives like the International Space Station, a modular spacecraft that serves as a science laboratory in low Earth orbit. Here, astronauts from different backgrounds and nationalities conduct experiments that benefit humanity as a whole, ranging from studying human health in space to testing new technologies that could aid future missions to the Moon or Mars. Moreover, such collaborations foster innovation. Different perspectives and varying technologies can lead to creative solutions that might not emerge within a singular effort. An example is the involvement of various space agencies in robotic missions, such as the international effort for Mars exploration, where different nations contribute specific instruments or landers. Each team brings a piece of the puzzle, working towards a common goal of unraveling the mysteries of the Martian surface. These partnerships also help spread the financial burden associated with lengthy and expensive missions. By sharing costs and technology, space agencies can embark on more ambitious projects. This cooperative spirit strengthens diplomatic ties and allows for shared knowledge and training, ultimately building a global community of scientists and engineers united in the quest for discovery. The combined efforts of international teams are not just pushing the boundaries of what we know about space, they are paving the way for the next generation of explorers. New missions that aim to return humans to the Moon and set sights on Mars are all part of a larger global vision. When countries work in harmony, the potential for space exploration becomes nearly limitless, inspiring awe and curiosity among people everywhere. Space agencies around the world are setting ambitious long-term goals for deep space exploration that reflect our desire to understand the universe and secure humanity's future among the stars. One major objective is to send human missions beyond the Moon, with Mars being the primary target. By establishing a human presence on Mars, these agencies aim to learn about the planet's past, search for signs of life, and gather valuable information to ultimately support future colonization efforts. In addition to Mars, exploration of asteroids is gaining traction. Agencies envision missions to study asteroids for their resources, which could be utilized for in-space construction and fueling, as well as understanding the history of our solar system. These small celestial bodies are time capsules from the early days of the solar system, holding clues about its formation and evolution. Moreover, advancements in technology are paving the way for missions to the outer planets, especially to places like Jupiter's moons. For instance, there is growing interest in the potential habitability of Europa, one of Jupiter's moons, where a subsurface ocean may harbor conditions suitable for life. Space agencies plan to deploy robotic missions that will conduct in-depth studies of these icy worlds and their environments. An overarching theme in deep space exploration is international collaboration. Space agencies aim to work together on these monumental tasks, pooling resources and expertise to foster global scientific progress. By uniting in this way, we enhance our capacity to explore and participate in humanity's next steps into the cosmos. Ultimately, the long-term goals of deep space exploration extend beyond mere scientific discovery. They include ensuring the survival of our species in the event of a global catastrophe, with the vision of creating self-sustaining habitats beyond Earth. The journey toward these goals will not only transform our understanding of life and the universe, but also inspire generations to come. The universe is filled with fascinating phenomena that challenge our understanding and pique our curiosity. One such mystery is dark matter. While we cannot see it directly, scientists have inferred its existence from its gravitational effects on galaxies. It appears to make up a considerable portion of the universe's mass, yet its exact nature remains unknown. Imagine a form of matter that is everywhere around us, and yet completely undetectable by our traditional instruments. Another captivating phenomenon is dark energy, which seems to drive the accelerated expansion of the universe. This elusive force appears to act in the opposite direction to gravity, pushing galaxies apart instead of pulling them together. The implications of dark energy are profound, questioning our understanding of the universe's fate and structure. Then there's the enigmatic behavior of fast radio bursts, brief, intense flashes of radio waves from distant galaxies. Their origin is still a topic of vigorous research. Some theories suggest they could be from neutron stars or black holes, but definitive explanations are still out of reach, leaving room for speculation and intrigue. Furthermore, we encounter gamma-ray bursts, which are the universe's most energetic explosions. While we understand they come from massive celestial events, such as the collapse of a star or the merge of neutron stars, the details behind these explosive phenomena are still being uncovered. Their powerful nature can outshine whole galaxies for a fleeting moment, making them both awe-inspiring and perplexing. Lastly, the very idea of cosmic strings poses a captivating puzzle. These hypothetical, one-dimensional defects in the fabric of space-time may have formed in the early universe and could stretch across vast distances. If they exist, they could warp space around them, influencing the motion of galaxies. However, as of now, finding evidence of these strings remains elusive, leaving researchers to ponder their significance in cosmic history. These unexplained phenomena illustrate not only the universe's complexity, but also the vast frontiers of knowledge waiting to be explored. Each mystery invites further investigation, promising new discoveries on our journey to understand the cosmos. When scientists encounter unexplained cosmic events, they approach them with a combination of curiosity, rigorous methodology, and collaborative effort. Think of cosmic events like puzzle pieces that have been thrown into disarray. To make sense of these scattered pieces, researchers start by gathering as much data as possible. This often involves using multiple observatories and telescopes around the world, each equipped with different technologies to capture a wide range of wavelengths, from visible light to radio waves and even gravitational waves. Once the initial data is collected, scientists analyze the observations. They look for patterns or anomalies that deviate from known celestial behaviors. This process is akin to detectives examining clues from a crime scene. Through simulation and modeling, researchers can recreate the conditions surrounding the event to better understand the possible causes and implications. Collaboration plays a vital role in these investigations. Scientists from various disciplines, such as astrophysics, cosmology, and even biotechnology, often bring unique perspectives and expertise. They form teams, sharing findings in conferences and publications, which fosters a broader understanding of the issue at hand. Peer review further strengthens the reliability of their conclusions. After the initial findings are presented, other experts evaluate the methodologies and interpretations, ensuring that the conclusions drawn are scientifically sound. This scrutiny is essential in a field where the mysteries of the universe can easily lead to speculation. As more information is gathered and theories tested, certain hypotheses may gain traction while others may be dismissed. The scientific community remains flexible and open to new information, continually adjusting its understanding of the cosmos. This iterative process allows scientists to gradually unveil the layers of mystery surrounding unexplained cosmic events, transforming curiosity into knowledge over time. Studying anomalies such as fast radio bursts offers a tantalizing glimpse into the workings of the universe. These sudden, powerful flashes of radio waves, lasting only a fraction of a second, are enigmatic signals that come from deep space. They are thought to originate from distant galaxies, yet their precise causes remain a mystery. By investigating these bursts, scientists are opening a window onto extreme environments and phenomena that we cannot replicate on Earth. Each fast radio burst provides clues about the conditions in their host galaxies and the processes at play, potentially revealing information about highly energetic astrophysical events, such as the merger of neutron stars or the collapse of massive stars. Furthermore, the way these radio signals travel through space can tell us about the intergalactic medium they pass through, including the density and composition of matter scattered throughout the cosmos. By analyzing their dispersion, scientists can infer how much matter is present throughout vast stretches of space. These enigmatic signals challenge our understanding of physics and cosmology. Each new discovery surrounding fast radio bursts helps refine our theories about the early universe, galaxy formation, and even the fundamental nature of space and time. Fast radio bursts could ultimately provide insights into the universe's most energetic and mysterious processes, pushing the boundaries of what we know about our cosmic home. Galaxies undergo a captivating journey of change over billions of years, marked by phases of growth, interaction, and transformation. Initially, galaxies form from vast clouds of gas and dust that collapse under their own gravity. This process is akin to how a snowball gathers more snow as it rolls down a hill. As more material is drawn in, these early galaxies build up their mass. As time progresses, galaxies don't merely sit in isolation. They frequently interact and collide with one another, leading to dramatic transformations. Imagine two dancers meeting on a stage, their movements blending and shifting as they come together. These collisions can result in the merging of galaxies, sometimes giving rise to new galaxy shapes, like the transition from spiral to elliptical forms. This astronomical choreography can trigger bursts of star formation as gas clouds collide and compress, igniting new stars in vibrant displays. Galaxies also evolve by exhausting their gas reserves. Over time, as stars form and burn bright, much of the available gas gets used up. Eventually, the galaxy shifts from a bustling hub of star creation to a more tranquil state, where star formation slows down significantly. This transition can lead to an aging population of stars, many of which spiral gracefully into the twilight of their life cycles. Additionally, the environment around a galaxy plays a crucial role in its evolution. The presence of neighboring galaxies, cosmic gas flows, and dark matter can all influence a galaxy's trajectory. Some galaxies find themselves in larger groups known as galaxy clusters, where gravitational interactions can strip away materials and alter their development. Throughout this long journey, galaxies also expel material into the surrounding cosmic environment. When massive stars end their lives in spectacular supernova explosions, they release heavy elements into space, seeding future generations of stars and potentially giving rise to planets and life. The life of a galaxy is a dynamic narrative that unfolds over vast timescales, shaped by gravitational forces, material interactions, and the ever-changing tapestry of the universe. Each galaxy's evolution tells a unique story, a testament to the complex processes that govern our cosmos. Galactic clusters are enormous gatherings of galaxies bound together by gravity. Imagine a bustling city made up of many interconnected neighborhoods, where each neighborhood represents a galaxy, complete with its own collection of stars, planets, and various cosmic phenomena. These clusters can contain anywhere from a handful to thousands of galaxies, all moving in unison through the vastness of space. Studying galactic clusters is crucial for several reasons. They serve as cosmic laboratories, helping astronomers understand the distribution of matter in the universe, both visible and dark. Dark matter, which makes up a significant portion of the universe's mass yet cannot be seen directly, exerts its influence primarily through its gravitational effects. By observing how galaxies within clusters move and interact, scientists can infer the presence and properties of dark matter. Furthermore, galactic clusters are vital for understanding the large-scale structure of the universe. They often mark the intersections between the vast voids of space and help illustrate how galaxies group together over cosmic time. By examining the formation and evolution of these clusters, researchers can gain insights into the history of the universe itself, including the processes that led to the formation of galaxies. Additionally, these clusters can be the sites of extreme physical conditions, where hot gas temperatures soar and powerful forces at play can lead to the birth of new stars. The study of galactic clusters enhances our comprehension of the life cycles of galaxies and the intricate dance of creation and destruction that shapes the cosmos. Ultimately, investigating these remarkable formations provides a deeper understanding of our universe's origin, evolution, and the mysterious forces that govern it. Galactic collisions are dramatic events that shape the evolution of galaxies over billions of years. When two galaxies come close to each other, their immense gravitational fields interact, pulling on each other's stars, gas, and dust. Initially, one might think that such massive structures would simply pass by each other, but gravitational forces can lead to significant alterations. As these galaxies draw closer, they begin to distort, forming long tidal tails, streaks of stars and gas that stream out due to gravitational interactions. These tidal forces initiate complex processes as clouds of gas collide and compress, which can trigger bursts of star formation. In these regions of dense gas, new stars ignite, adding brightness and activity to the once quiet galaxies. If the encounter is strong enough, the galaxies may merge completely, combining their cores. This transformation results in a new, larger galaxy, often a chaotic mix of the two original structures. The merging process can lead to a variety of shapes, including spirals, ellipticals, and irregulars, depending on the properties of the colliding galaxies and the angle of collision. Additionally, these collisions can influence the distribution of dark matter, which is the unseen mass that comprises a large part of a galaxy's total mass. As galaxies collide, the dynamics of dark matter halos, regions surrounding galaxies that contain dark matter, can rearrange, potentially altering gravitational stability and affecting future interactions. Collisions between galaxies are significant events that catalyze star formation, create new galaxy types, and transform the galactic landscape. They illustrate the dynamic and interconnected nature of the universe, where the fate of one galaxy can be forever altered by the presence of another. Astronomers have developed a fascinating ability to unravel the history and composition of the universe by studying light. When we look into the cosmos, we are not just seeing distant stars and galaxies. We are observing the light they emit or reflect, which carries vital information. Light behaves like a messenger from the past, reaching us after traveling immense distances, sometimes taking millions or even billions of years to arrive. The first tool in an astronomer's arsenal is the spectrum. When light from a celestial object passes through a prism, it spreads into a rainbow of colors. Each color corresponds to a different wavelength, and these variations can reveal the object's chemical makeup. Each element, like hydrogen or helium, emits or absorbs light at specific wavelengths, creating a unique fingerprint. By examining these patterns, astronomers can determine which elements are present, revealing much about the star or galaxy's composition and the nuclear processes powering them. Moreover, the way light behaves as it travels through space, its redshift or blue shift, provides essential clues about an object's movement. When an object moves away from us, the light it emits stretches, shifting toward the red end of the spectrum. This is known as redshift. Conversely, if it moves closer, the light compresses, shifting toward the blue end. This principle helps astronomers determine the speed at which galaxies are receding from us, underscoring the expansion of the universe itself. Further, the study of light allows astronomers to probe the universe's history. Light from faraway celestial events, such as the explosion of a supernova or the formation of a black hole, can provide snapshots of events that happened long ago. By analyzing this light, scientists can piece together a timeline spanning billions of years, giving insights into the life cycle of stars and the evolution of galaxies. Light is not merely illumination. It is a powerful tool, providing insights into the universe's past and offering a deeper understanding of the fundamental processes at play within it. Through their meticulous studies of light, astronomers eloquently weave together the narrative of our vast cosmos. Redshift and blue shift serve as powerful indicators of cosmic motion, illuminating the movement of celestial bodies in the universe. Imagine light traveling through space as a wave, much like ripples in a pond. When an object in space, such as a star or galaxy, moves away from us, the light it emits is stretched out, resulting in a redshift. This shift towards the red end of the spectrum indicates that the object is receding, akin to how the sound of a siren lowers in pitch as an ambulance drives further away. Conversely, when an object moves toward us, its light waves are compressed, creating a blue shift. This shortening of wavelength resembles the rising pitch of a siren as it speeds closer. These shifts in light are not merely aesthetic, they provide crucial evidence for understanding the motion and speed of celestial objects. By analyzing the redshift or blue shift of light from distant galaxies, scientists can infer their velocity relative to Earth. This insight is fundamental for uncovering the universe's expansive nature. The discovery that most galaxies exhibit a redshift led to the realization that the universe is expanding, a revolutionary idea that reshaped our understanding of cosmology. Furthermore, redshift and blue shift are essential in various astronomical applications, including the study of the universe's evolution, the behavior of stars in different gravitational fields, and the life cycle of galaxies. These color shifts thus act as cosmic signposts, guiding us through the intricate and dynamic tapestry of the universe. Quasars are among the most ancient and powerful objects in the universe, acting like cosmic time capsules that allow us to peer back into its history. To understand this, imagine looking at a star in the sky. When you see its light, you're not seeing it as it is now, but as it was when that light first began its journey. With quasars, this concept takes on extraordinary significance. A quasar is the incredibly bright center of a galaxy, powered by a supermassive black hole consuming material at an astonishing rate. As this material spirals in, it emits massive amounts of energy, making quasars visible over vast distances. Importantly, many quasars we observe today originated billions of years ago, when the universe was much younger. This means that when we look at their light, we are also looking back in time. The light from a quasar that we see today may have started its journey just a few 100 million years after the Big Bang, giving astronomers invaluable information about the conditions of the early universe. By studying the light emitted by quasars, researchers can uncover details about the formation of galaxies, the distribution of matter, and the evolution of cosmic structures over time. Moreover, quasars often emit unique fingerprints in their light spectrum, revealing the composition of the universe during the epochs they originated from. Analyzing these spectral features allows scientists to unravel the mysteries of elements present in those distant times, shedding light on how the universe evolved from its hot, dense beginnings to the vast and complex expanse we see today. Quasars serve not just as distant beacons, but as windows into a fascinating journey through cosmic history. Mathematics serves as the universal language of science, especially when it comes to understanding the cosmos. Think of mathematics as a toolkit, providing scientists with the means to describe, model, and predict phenomena beyond our planet. It helps represent complex ideas in a clear and logical way, allowing astronomers and physicists to explore the intricacies of the universe. For instance, consider the movements of celestial bodies. They do not just linger in space, they move according to certain patterns influenced by gravity. Scientists rely on mathematical equations to describe these movements. By understanding the relationships between different bodies, they can determine how planets orbit stars or how galaxies interact. This predictive power can reveal when eclipses will happen or when a comet might be visible from Earth. Mathematics also plays a crucial role in understanding the fundamental forces of the universe. Take the concept of gravity. Isaac Newton's laws of motion, expressed mathematically, allow us to calculate how objects will move under the influence of gravity. This foundational work laid the ground for further scientific advances, including Albert Einstein's theories, which introduced a more complex understanding of gravitational interactions. Einstein's equations describe how massive objects impact the fabric of space and time, further enriching our predictions of cosmic events. Moreover, mathematics is vital for analyzing data collected from telescopes and space probes. Scientists gather vast amounts of information, which can be overwhelming. By applying statistical methods and algorithms, they can sift through dust and noise to uncover significant patterns, potentially leading to groundbreaking discoveries about dark matter, exoplanets, and the expansion of the universe. Additionally, simulations powered by mathematical models allow scientists to explore theoretical scenarios that may not yet be observable. For example, models of the early universe help researchers understand how the cosmos evolved from a dense, hot state into its current form, which includes the formation of galaxies and the distribution of cosmic structures. Mathematics is at the heart of unraveling the mysteries of the universe. It guides scientists in making predictions, testing theories, and ultimately revealing the extraordinary complexities of the cosmos that shape our very existence. Without this powerful tool, our understanding of the universe would remain limited, much like trying to navigate without a map. Mathematical models have been fundamental in shaping our understanding of the universe, allowing us to translate complex observations into comprehensible concepts. One of the most transformative models is the theory of gravity, formulated by Sir Isaac Newton. This framework simplified the understanding of planetary motions and laid the groundwork for how celestial bodies interact through gravitational forces. It presented the idea that objects attract each other based on their mass and the distance between them, providing a clear mechanism for explaining movements in our solar system. As we advanced, Albert Einstein's theory of general relativity revolutionized this understanding. It introduced a new perspective, showing that gravity is not just a force, but rather a curvature of space and time around massive objects. Imagine placing a heavy ball on a stretched rubber sheet. The sheet begins to dip and curve, demonstrating how massive bodies like planets warp the fabric of the universe. This model elegantly explains phenomena such as the bending of light around massive stars and the gravitational effects observed in galaxy clusters. Another significant contribution comes from quantum mechanics, which describes the behavior of particles at tiny scales. This field employs sophisticated mathematical frameworks to explain how particles interact, enabling predictions that have been confirmed through experiments. Concepts such as wave-particle duality and entanglement have opened new avenues in understanding the fundamental workings of the universe, highlighting the complex dance of matter and energy. Cosmological models, like the Big Bang theory, use mathematical principles to depict the universe's expansion from an incredibly hot and dense state. Equations in this context provide insights into how the universe began, how it has evolved, and what its ultimate fate may be. By applying these frameworks, scientists have also explored concepts like dark matter and dark energy, mysteries making up a significant portion of the universe, yet remaining elusive. Through these mathematical models, we are not just cataloging celestial phenomena. We are piecing together a coherent narrative of the universe's complex and intricate structure. Each model builds upon observations, connecting them through richly interwoven concepts that continue to guide our exploration of the cosmos, forever expanding our comprehension of the grand tapestry that surrounds us. Mathematical theories have been the backbone of our exploration of space, guiding everything from our understanding of celestial movements to the engineering of spacecraft. At the very heart, mathematics provides a universal language that allows scientists and engineers to make precise predictions about the behavior of objects in space. For example, the laws of motion developed by Isaac Newton describe how objects move under the influence of gravity. These laws inform everything from how satellites orbit Earth to how spacecraft navigate the vast reaches of our solar system. As we ventured beyond our planet, we faced new challenges that required innovative mathematical thinking. For instance, predicting the trajectory of a spacecraft involves complex calculations that take into account gravitational forces from multiple celestial bodies and the spacecraft's velocity. This means utilizing mathematical models that can simulate these variables to ensure successful missions. Moreover, the advent of Einstein's theory of relativity introduced a revolutionary understanding of time and space. This theory not only allowed us to comprehend the structure of the universe, but reshaped how we think about distances and the fabric of space itself. As we study phenomena like black holes or the expansion of the universe, mathematics helps us quantify and visualize concepts that are otherwise abstract and enigmatic. Mathematics also plays a crucial role in astrophysics, where it helps explain the behavior of stars, galaxies, and cosmic events. Through mathematical models, scientists can analyze data collected from telescopes and sensors, leading to discoveries about the formation of the universe and the fundamental forces that govern it. Without mathematics, our understanding of space would remain limited. It is through mathematical theories that we formulate questions, conduct experiments, and ultimately expand the boundaries of our knowledge, propelling us further into the cosmos and unraveling the mysteries of the universe. Our understanding of the universe is vast, yet still shrouded in mystery. Despite significant advancements in technology and knowledge, there are several areas where questions remain unanswered and theories are still being formulated. Firstly, the nature of dark matter and dark energy is a critical gap in our comprehension. Scientists have established that these two components make up about 95% of the universe's total mass energy content. Yet, their precise properties and how they interact with ordinary matter remain elusive. Dark matter is thought to exert gravitational effects on galaxies and galactic clusters, while dark energy seems to drive the universe's accelerated expansion. Without direct detection or a deeper understanding of these phenomena, we find ourselves in a state of uncertainty. Additionally, our grasp of the universe's earliest moments is limited. The theories of the Big Bang suggest a singularity, a point of infinite density where current physical laws break down. What occurred during this time and how the universe underwent its rapid expansion, known as cosmic inflation, is still speculative, leaving us with a gap in understanding the conditions that shaped everything we now observe. Furthermore, the enigma of black holes presents challenges, particularly regarding their interiors. Although we have strong theories to describe them outside their event horizons, we do not know what happens inside these boundaries. Concepts such as the information paradox, which questions how information is preserved when matter falls into a black hole, continue to provoke debate. The integration of quantum mechanics and general relativity is another frontier that remains unresolved. These two pillars of physics have successfully explained many phenomena, but are fundamentally incompatible in their current forms. Scientists are striving for a unifying theory that could harmonize the very small, the realm of particles, with the very large, the structure of the cosmos. Finally, the quest for understanding life beyond Earth also highlights our current limits. While we have identified potentially habitable planets and the building blocks of life in various environments, our exploration is still in its infancy. The search for extraterrestrial intelligence remains an open question, reflecting both our curiosity and our limitations. These challenges illustrate that while we have made remarkable progress in uncovering the universe's secrets, much remains to be explored and understood. The quest for knowledge continues to push the boundaries of science, often leading to more questions than answers, but driving humanity ever forward in our search for truth about the cosmos. In the realm of cosmic exploration, uncertainty is a constant companion. Scientists approach this vast unknown with a combination of careful planning, analytical thinking, and innovative technology. First, they utilize the scientific method, which allows them to form hypotheses and test them through experiments and observations. This structured approach provides a foundation for understanding complex phenomena, even when data is scarce. One key strategy is the use of simulations and models. By creating virtual representations of cosmic events or environments, like the interaction of celestial bodies or conditions on distant planets, scientists can predict behaviors and outcomes. These models are anchored in well-established principles of physics, making them helpful guides as researchers navigate the unpredictability of the universe. Collaboration is another powerful tool. Scientists from diverse fields, such as astrophysics, planetary science, and engineering, come together to share knowledge and resources, effectively expanding their understanding. This interdisciplinary teamwork allows for a richer exploration of ideas and solutions, particularly when confronting the unexpected challenges that arise. When it comes to data collection, spacecraft and telescopes equipped with advanced instruments are essential. These tools gather extensive amounts of information across various wavelengths, capturing details that the human eye cannot see. However, interpreting this data can be tricky, as it often contains ambiguity. To combat this, scientists rely on statistical methods and peer reviews, where findings are scrutinized and refined by their peers, ensuring that conclusions are well supported and valid. Flexibility is also critical. The vastness of space can present surprises, like the detection of a new celestial body or unexpected conditions on a mission. A successful scientist remains open to adjusting their theories and methods in light of new evidence, embracing the process of learning and discovery. By combining structured methodologies, technological innovation, collaborative efforts, and adaptability, scientists effectively manage the uncertainties inherent in cosmic exploration. In a universe filled with infinite possibilities, these practices allow them to continue their quest for knowledge amid the unknown. Cosmology, The study of the universe's origin and evolution still harbors numerous unsolved questions that pique the curiosity of scientists and enthusiasts alike. One of the most pressing enigmas is the nature of dark matter. We know it exists due to its gravitational effects on galaxies and cosmic structures, yet its true composition remains elusive. What exactly is this unseen mass? Could it be composed of exotic particles that are yet to be discovered in our laboratories? Another significant mystery lies in dark energy, a force driving the universe's accelerated expansion. While we can observe its effects, the fundamental nature of dark energy is still unknown. Is it a constant energy density spread throughout space, or does its strength change over time? Understanding dark energy could reshape our entire comprehension of the cosmos. Additionally, the precise mechanics of the Big Bang itself remain a topic of immense interest. What triggered this momentous event, and what was the universe like in its earliest moments? The conditions that existed before and during this rapid expansion are still not fully understood, leading scientists to explore various theories, from quantum fluctuations to multidimensional models. The quest for a unified theory that reconciles general relativity, which governs large-scale structures and gravitational forces, with quantum mechanics, which describes the behavior of the smallest particles, is another frontier. This is often referred to as the challenge of quantum gravity. How do these two frameworks interact, particularly under extreme conditions like those found at the center of black holes or during the Big Bang? Lastly, there is the question of the fate of the universe. With expansion occurring at an ever-increasing rate, will the universe continue expanding indefinitely, or will there be a point where it might reverse, collapsing back in on itself? Exploring these potential scenarios is not just academic. It could ultimately define the very future of everything we know. These questions, along with others, fuel profound discussions among cosmologists. Each mystery carries the potential to unveil deeper truths about our universe, shaping our understanding of existence itself. Early astronomers significantly reshaped our understanding of the cosmos, laying the foundation for how we perceive our place in the universe today. In ancient times, civilizations looked at the night sky and saw celestial bodies as part of their myths and deities. The first major shifts came from philosophical thinkers, such as the Greeks, who began to propose ideas about the nature of the universe. They shifted the focus from mythological explanations to more scientific approaches, contemplating whether the Earth was at the center of it all or simply one of many planets in motion. The introduction of the heliocentric model by Nicholas Copernicus was groundbreaking. He suggested that the Sun, not the Earth, was at the center of the solar system. This challenged deep-rooted beliefs and forced humanity to reconsider its significance within the vastness of the cosmos. Following Copernicus, figures like Johannes Kepler built on his ideas, developing laws that described how planets moved in elliptical orbits. Kepler's work added mathematical precision to the understanding of celestial movements, emphasizing that the universe operated according to natural laws. Galileo Galilei's use of the telescope provided clear evidence that supported the heliocentric model. He observed the moons of Jupiter and the phases of Venus, which could not be reconciled with the Earth-centered model. Galileo's discoveries opened the door to a new era of observational astronomy, enabling a more detailed study of celestial bodies. His findings not only changed how we understand planetary motion, but also highlighted the importance of empirical evidence in science. Furthermore, Sir Isaac Newton's formulation of gravity articulated how celestial bodies interacted with one another through gravitational forces. This not only explained the motions of planets, but also provided a framework for understanding the behavior of objects both on Earth and in space. His laws of motion and universal gravitation combined to suggest a universe that was predictable and governed by specific laws, contrasting sharply with earlier ideas of a chaotic and random cosmos. These early discoveries and theories shifted humanity's perspective from an Earth-centered, anthropocentric view to one that recognizes a vast and complex universe, full of wonders and governed by natural laws. They sparked questions that continue to drive exploration and curiosity, ultimately laying the groundwork for modern astronomy and our ongoing quest to understand the universe's mysteries and our place within it. Ancient civilizations held a profound fascination with the cosmos, interpreting celestial events as meaningful and often divine phenomena. These events, such as solar eclipses, meteor showers, and the movements of planets, were intertwined with their mythologies, agricultural practices, and cultural rituals. For them, the skies were not just a backdrop, but a living tapestry that communicated the will of the gods and offered guidance for daily life. Take the ancient Egyptians, for example. They revered the sun as a powerful deity, with cosmic events considered predictors of earthly happenings. Their impressive pyramids were aligned with stellar phenomena, showcasing their deep understanding of astronomy. The artifact known as the Shabaka stone preserves a creation myth that connects the cosmos and the origin of the world. Similarly, the Mayans constructed elaborate observatories and created precise calendars, allowing them to predict solar and lunar eclipses with astounding accuracy. Their artifacts, including intricately carved stelae and pottery, reflect their celestial interpretations, weaving astronomy into their culture and religion. In Mesopotamia, the Babylonians recorded astronomical observations on clay tablets, connecting their observations to agriculture, predicting weather patterns and timing agricultural cycles. Their astronomical artifacts depict constellations and planetary paths, underscoring the significance they placed on understanding the heavens. These artifacts provide a window into the minds of ancient peoples, revealing how they interpreted cosmic events. The tools they developed for observational astronomy, such as sundials and simple astrolabes, highlight their ingenuity and desire to comprehend the universe. Even today, monuments like Stonehenge stand as enduring symbols of humanity's relationship with the cosmos, serving both as a calendar and a place of ritual. Through these remnants, we gain insight into how ancient civilizations not only navigated their lives by celestial events, but also built their worldviews around them, creating a rich tapestry of beliefs, practices, and legacies that continue to intrigue us. The landscape of cosmology has been dramatically transformed through several key observational breakthroughs. Each of these milestones has provided new insights and challenged existing theories about the universe. One pivotal moment came with the invention of the telescope in the early 17th century. Astronomers like Galileo Galilei used this new instrument to deepen our understanding of celestial bodies. With improved visibility, he discovered moons orbiting Jupiter and observed the phases of Venus, which supported the heliocentric model, suggesting that the Earth revolves around the Sun. Fast forward to the 20th century, the discovery of cosmic microwave background radiation revolutionized our understanding of the universe's beginnings. This faint glow, which fills the universe, is the afterglow of the Big Bang, offering compelling evidence for the Big Bang theory and establishing a framework for understanding the universe's early moments. Another significant advancement occurred with Edwin Hubble's observations in the 1920s. He found that distant galaxies were moving away from us, leading to the realization that the universe is expanding. This observation was crucial as it provided the groundwork for the concept of an expanding universe and accelerated the acceptance of the Big Bang model. In the late 20th century, precise measurements of supernovae and the discovery of dark energy reshaped our comprehension of the universe's fate. Observations showed that the expansion of the universe is not only continuing, but is also accelerating, driven by an enigmatic force dubbed dark energy. This finding has profound implications for how we think the universe will evolve over time. Furthermore, advancements in technology, like the development of space-based observatories such as the Hubble Space Telescope, have allowed for clearer and more comprehensive observations beyond the limitations of Earth's atmosphere. These observations have revealed the existence of exoplanets, reshaping our views on planetary systems and the potential for extraterrestrial life. Each of these breakthroughs did not merely add to our knowledge, they fundamentally shifted our theoretical frameworks. With every advancement, the cosmos became a little less mysterious, yet infinitely more complex, inviting scientists to continue exploring the intricate tapestry of the universe. Each discovery represents a step forward in our quest to understand the cosmos, demonstrating how observation can lead science to question, refine, and expand its theories in response to new evidence. Quantum physics and cosmology might seem like separate realms, but they are deeply intertwined in our quest to understand the universe. At the core of quantum physics lies the study of the smallest particles and their behaviors, which often defy our everyday experiences. On the other hand, cosmology focuses on the grand scale of the universe, the birth, evolution, and large-scale structure of cosmic phenomena. One of the key intersections occurs in the realm of the early universe. Shortly after the Big Bang, the universe was an incredibly hot and dense place where quantum effects were paramount. Here, the laws of quantum mechanics helped shape the very fabric of space-time. When we look at the beginning of everything, models that incorporate both quantum mechanics and the dynamics of the universe become essential to explain what happened during those first moments. Additionally, concepts such as black holes bring these fields together again. The event horizon of a black hole is a point beyond which nothing can escape. According to quantum physics, information about the particles that fall into a black hole should not be lost, challenging our understanding of reality. This dilemma has resulted in ongoing debates and theories attempting to reconcile the principles of quantum mechanics with the gravitational pull of black holes in cosmology. Furthermore, the concept of quantum fluctuations provides insight into the formation of structures in the universe. In the early moments of cosmic inflation, a rapid expansion following the Big Bang, tiny quantum fluctuations were stretched across the universe. These fluctuations eventually seeded galaxies and large-scale structures, directly linking quantum processes to the cosmos we observe today. The intersection of quantum physics with cosmology is fundamental to our understanding of existence itself. Whether probing the mysteries of the early universe, unraveling the complexities of black holes, or explaining the formation of galaxies, the dance between the minuscule and the monumental continues to reveal the intricate tapestry of reality. Quantum phenomena introduce several intriguing challenges to how we traditionally understand cosmic events, fundamentally altering our perception of reality. At the core of these phenomena is the concept of entanglement, where particles become interconnected in such a way that the state of one can instantly affect the state of another, no matter the distance separating them. This defies the intuitive sense of locality, suggesting that information can travel faster than the speed of light. Another significant concept is superposition, where particles exist in all possible states until they are observed. This notion raises questions about the nature of reality and observation, proposing that the universe might hold multiple configurations simultaneously until it interacts with something that causes a single outcome. This principle of superposition has implications on the very fabric of space and time, causing scientists to reconsider how events unfold on cosmic scales. Black holes also present a quantum enigma. According to classical physics, once something crosses the event horizon of a black hole, it is lost forever. However, quantum mechanics introduces the idea of Hawking radiation, suggesting that black holes can emit radiation and potentially lose mass over time, leading to their gradual evaporation. This challenges the traditional understanding of these cosmic giants as eternal traps. Additionally, the behavior of particles in the universe at substantial distances, such as in cosmic microwave background radiation, hints at the influence of quantum mechanics on the overall structure of the cosmos. The mixing of quantum physics with general relativity in understanding phenomena, such as the expansion of the universe, creates a complex interplay that remains unresolved. These quantum phenomena not only enrich our understanding of the universe, but also challenge the very foundations of physics as we know it, urging a re-evaluation of concepts that have long stood as pillars of cosmology. As we explore these mysteries further, we will inevitably deepen our grasp of the cosmos and our place within it. Quantum theories delve into the behavior of matter and energy at the smallest scales, and they open a fascinating window into understanding anomalies in deep space. At vast distances, where traditional physics sometimes struggles, the peculiarities of quantum mechanics could provide insights into phenomena that seem out of place, such as unusual gravitational effects or the behavior of dark matter. Imagine the universe as a vast and intricate tapestry. While classical physics outlines the overall structure, quantum mechanics shows us the threads that weave through it at a micro level. One significant anomaly observed in deep space is the apparent disparity between the visible matter and the gravitational effects we observe. This suggests that something unknown is influencing the cosmos, possibly dark matter. Quantum theories propose that particles we can't yet fully detect may be interacting with visible matter in unforeseen ways, creating unaccounted-for gravitational influences. Furthermore, quantum entanglement, the idea that particles can become connected in ways that transcend traditional distances, might imply that events occurring light-years away could still have an instantaneous connection, hinting at a deeper fabric of reality than we currently comprehend. This could offer explanations for mysterious energy signatures or fluctuations detected in cosmic backgrounds. In addition, quantum fluctuations, the idea that energy levels are not constant but change rapidly at microscopic levels, could influence fields and particles in space, leading to unexpected outcomes in the observed behavior of galaxies or cosmic radiation. This perspective allows scientists to reconsider anomalies as not merely oddities, but as clues that could unlock new understanding of the universe's structure and origins. Ultimately, quantum theories provide a toolkit to probe the deepest mysteries of space, suggesting that by examining the very small, we just might decode the cosmic puzzles that have bewildered astronomers for centuries. Computer simulations act as powerful tools for visualizing and understanding the vast and complex structures of the cosmos. Given the immense scale of the universe and the intricate physics involved, it becomes challenging to grasp these phenomena through observation alone. Simulations allow scientists to create three-dimensional representations of cosmic events and entities, which can reveal patterns and relationships that are not always apparent in real-life observations. Through these simulations, researchers can model the behavior of galaxies, star formations, and even the dynamics of dark matter. Imagine this as a virtual laboratory where the laws of physics can be applied to create scenarios that mimic our universe. By adjusting the parameters of these simulations, like the amount of matter or energy involved, scientists can explore various outcomes and test different theories without needing to wait eons for events to occur naturally. Additionally, simulations help in visualizing the early universe. They can recreate conditions just moments after the Big Bang, allowing scientists to examine how the universe expanded and evolved, providing crucial insights into its formation. These virtual experiments can also address questions about the structure of the cosmos, like how galaxies cluster together and the role gravity plays in shaping the universe. Ultimately, simulations serve a dual purpose. They provide a platform for testing ideas and hypotheses while opening up a window into the universe's workings, transforming abstract concepts into tangible visuals. This approach helps both scientists and enthusiasts to engage more deeply with the material, fostering a better understanding of the universe we inhabit. Simulations play a crucial role in testing theories of cosmology by allowing scientists to recreate and analyze the vast complexities of the universe in a controlled setting. Think of simulations as virtual laboratories, where cosmic events can be modeled in detail without the limitations of time and space that real-world observations face. By inputting initial conditions influenced by our current understanding of physics, researchers can explore how structures in the universe evolve over billions of years. For instance, they can simulate the gravitational interactions among galaxies, the formation of stars, or the movement of dark matter. Through these simulations, scientists can visualize phenomena that are not always observable, such as the merging of galaxy clusters or the behavior of matter surrounding black holes. The true power of simulations lies in their ability to generate predictions that can be compared against observational data. For example, if a simulation predicts the distribution of galaxies in a particular region of space, and that aligns closely with what telescopes observe, it strengthens their underlying theories. Conversely, significant discrepancies can lead to re-evaluating those theories or prompting questions about the physical laws governing the cosmos. Moreover, as computational technology advances, simulations grow increasingly sophisticated, enabling researchers to incorporate complex factors such as cosmic inflation or the influence of dark energy. This iterative process of running simulations, refining theoretical models, and comparing results with empirical data is instrumental in deepening our understanding of the universe. Ultimately, simulations help bridge the gap between abstract theoretical concepts and tangible astronomical phenomena, making them an indispensable tool in cosmological research. Researchers often use computer simulations to explore cosmic phenomena that are beyond our direct observation. These simulations act like virtual laboratories where scientists can recreate complex processes that occur in the universe, such as the formation of galaxies, the behavior of black holes, or the explosion of supernovae. To create these simulations, scientists begin by establishing physical models based on our current understanding of the laws of physics. Principles like gravity, electromagnetism, and thermodynamics. They convert these principles into mathematical equations that describe how different components of cosmic systems interact over time. Next, they utilize powerful supercomputers to solve these equations. The immense computational power allows them to simulate billions of particles representing stars, gas, and dark matter, each interacting according to the laws of physics. As the simulation progresses, researchers can witness the evolution of galaxies or the merger of massive black holes, gaining insights into processes that take millions or even billions of years in real life. In addition to these simulations, researchers often compare their findings with observable phenomena. For instance, they look for matching patterns or similar behaviors in real astronomical data, such as the light emitted by distant objects or the gravitational waves produced by astronomical events. By validating their simulations against real observations, scientists can refine their models and build a more accurate understanding of the universe. These techniques allow researchers not only to visualize cosmic phenomena, but also to make predictions about future observations. Through this method, they effectively bridge the gap between known physics and the mysterious realms of the universe that remain shrouded in darkness, enabling us to understand cosmic events that are otherwise elusive. Meteorites, asteroids, and comets are fascinating components of our cosmic ecosystem, each playing unique roles in shaping the solar system and influencing life on Earth. Starting with asteroids, these rocky remnants from the early solar system are primarily found in the main belt located between Mars and Jupiter. They serve as time capsules, containing clues about the conditions and materials present during the solar system's formation. Scientists study asteroids to understand the building blocks that potentially contributed to the creation of planets. Some asteroids even contain valuable resources, such as metals and minerals, which may one day provide significant benefits to humanity through space mining. Moving beyond the rocky bodies, we find comets, often characterized by their icy cores surrounded by gas and dust. Originating from the distant reaches of our solar system, particularly the Kuiper Belt and the Oort cloud, comets are like dirty snowballs floating through space. When they approach the sun, the heat causes their ice to vaporize, creating spectacular tails that can stretch for millions of kilometers. Comets have historically been viewed as harbingers of change, and they may have played a critical role in delivering water and organic compounds to Earth billions of years ago. This delivery could have been instrumental in fostering the conditions necessary for life. Meteorites, which are fragments from asteroids or comets that survive their fiery fall through Earth's atmosphere, offer direct samples of these celestial objects. Studying meteorites provides insight into the materials that formed our planet and others, revealing information about the early solar system's chemical makeup. Some meteorites contain amino acids, the building blocks of life, suggesting that the ingredients for life might be more widespread in the universe than we previously thought. Together, meteorites, asteroids, and comets are vital players in the grand narrative of the universe. They help scientists decipher the history of our solar system while posing questions about life beyond Earth. Their interactions can also significantly influence planetary atmospheres and environments through impacts, illustrating their role as both creators and destroyers in this cosmic drama. Celestial objects play a vital role in unraveling the intricate history of our solar system's formation. Each type of celestial body, from asteroids and comets to moons and planets, serves as a time capsule, preserving clues about the conditions prevalent during the early stages of our solar system. Asteroids, for instance, are remnants from the primordial disk of material that surrounded the young sun, containing the same building blocks that once formed the planets. By studying their composition and structure, scientists can gather insights into the chemical processes that took place during the solar system's infancy. These rocky bodies reflect the materials that didn't coalesce into larger planets, helping to define the characteristics of the early solar environment. Comets, with their icy compositions, provide additional perspective. Often originating from the distant reaches of the solar system, comets carry water and organic compounds, which are thought to be essential ingredients for life. When comets encounter the sun, they release gas and dust, creating spectacular tales that can be analyzed to learn about early solar system chemistry and the potential for habitability. Moreover, observations of moons, particularly those of the gas giants, reveal diverse geological and atmospheric processes that hint at the dynamic evolution of our solar neighborhood. For example, moons like Europa have subsurface oceans, suggesting that these environments may harbor the conditions necessary for life, prompting questions about the distribution of life in the universe. Studying these celestial objects through telescopes and spacecraft missions has also illuminated theories of planetary formation and migration. By analyzing their orbits, scientists can piece together the gravitational interplay that shaped the configuration we see today. Thus, celestial objects not only constitute the building blocks of our solar system, but also serve as vital sources of information, guiding our understanding of how it formed and evolved over the billions of years. The study of space rocks, often referred to as asteroids and meteoroids, holds crucial insights regarding potential threats to our planet. These celestial bodies can vary in size and composition, and many of them venture close to Earth's orbit. By closely examining their physical characteristics, scientists can gather valuable information about their trajectory, structure, and what might happen if one were to collide with our planet. Firstly, understanding the orbits of these space rocks allows researchers to predict their paths. This knowledge is essential for identifying which objects could pose a danger to Earth in the future. The gravitational influences of other celestial bodies must be considered, as even a small change in trajectory can lead to significant shifts in their paths over long periods. In addition to their orbits, the composition of asteroids provides insights into their origins and histories. Some asteroids are remnants of the early solar system, holding clues about the conditions that existed when the planets were formed. By learning more about these materials, scientists gain a better understanding of what types of objects might threaten Earth and how their impacts may differ based on their size and structure. Furthermore, studying the effects of past impacts on Earth helps us comprehend the potential damage that could occur from future collisions. Evidence from craters on our planet and the Moon serves as a record of historic events, illustrating how different sizes and speeds of meteoroids have triggered a range of environmental consequences, from localized destruction to global catastrophes. Ultimately, the insights gained from the study of space rocks enable us to devise strategies and potential defensive measures. By mapping the locations and movements of these objects, scientists can work on early warning systems and explore methods for diverting a threatening asteroid should one be found on a collision course with Earth. Through this ongoing research, we enhance our preparedness for any potential cosmic threats, ensuring the safety of our planet and its inhabitants. Scientists study the evolution of celestial bodies over vast cosmic timescales by employing a combination of observational techniques, theoretical models, and computer simulations. To begin with, astronomers gaze deeply into the universe using powerful telescopes that capture light across different wavelengths, from visible to infrared and radio waves. These observations reveal a treasure trove of information about the age, composition, and dynamics of stars, planets, and galaxies, helping scientists understand how these entities form and evolve. Another vital approach involves the study of light emitted or absorbed by celestial bodies. The spectrum of light enables scientists to determine an object's temperature, chemical composition, and velocity. For instance, by identifying specific patterns in the light, they can ascertain whether a star is moving towards or away from us, which is crucial for understanding gravitational interactions over time. Beyond observations, theoretical models play a significant role in predicting how celestial bodies evolve. These models incorporate the laws of physics, including gravity, nuclear fusion, and thermodynamics, to simulate processes such as star formation and galaxy mergers. By adjusting different variables, scientists can explore a range of scenarios, gaining insights into the life cycles of stars, the birth of new planetary systems, and the eventual fate of galaxies. Furthermore, computer simulations allow astronomers to model complex interactions in space more accurately. These simulations can depict how celestial bodies collide, change composition, or even how entire galaxies may evolve and interact over billions of years. By comparing simulations with observed phenomena, researchers can refine their models and enhance our understanding of the universe's history. Finally, studying ancient celestial objects, such as stars known as population Ixu stars, which are among the oldest in the universe, gives insight into the conditions of the early cosmos. By examining the light they emit, scientists can deduce the elemental makeup of the early universe, revealing how it has changed over time. This multifaceted approach, blending observation, theory, and simulation, provides a comprehensive means of exploring the evolution of celestial bodies across the eons. As we look far into the future of our universe, a striking transformation awaits the cosmic landscape. Over an immeasurable span, galaxies will reshape, collide, and even merge. Our own Milky Way, for instance, is on a collision course with the Andromeda Galaxy, which will create a frenzy of star formation and gravitational interactions. This event is expected to occur in approximately 4 billion years, yet it is merely the start of a more chaotic cosmic dance. Beyond these galactic encounters, the fates of individual stars will also redefine the sky. Stars will burn out, some ending their lives in spectacular supernova explosions, while others collapse into neutron stars or black holes. The remnants of these stellar corpses will add to the complex tapestry of the cosmos, introducing dense regions of gravity that can warp nearby space-time. As time stretches onward, galaxies will gradually grow more distant from one another. The expansion of the universe, driven by a mysterious force known as dark energy, will lead to a point where our local group of galaxies, including the Milky Way, may become one of the few remaining visible clusters in a dark and empty space. Eventually, all but the nearest galaxies will slip beyond our ability to see them, causing our night sky to evolve into an ocean of darkness. In the ultra-distant future, about 100 trillion years from now, the universe will enter a state known as the Cosmic Dark Age. With stars extinguished and galaxies drifting apart, the remaining matter will become scattered, leaving behind a quiet universe filled with black holes and cold remnants of stars. This will culminate in a scenario known as heat death, where everything stabilizes at a uniform temperature, marking a stillness in the once vibrant cosmic landscape. Thus, the future holds a universe vastly different from the one we witness today, one that tells a story of evolution, decay, and a slow fade into a tranquil darkness. As we perceive time on a cosmic scale, these changes unfold over unimaginable durations, allowing us to appreciate both the beauty and transience of our ever-evolving universe. Cosmic time scales introduce a fascinating perspective that contrasts sharply with our earthly understanding of time. On our planet, we typically measure time in hours, days, and years, governed by the routine rhythm of the sun rising and setting. This familiar cycle offers a comforting predictability. However, when we step into the vastness of the cosmos, time begins to stretch and warp in ways that can be quite surprising. In the universe, events unfold over millions or even billions of years. For example, the life cycle of stars, from their formation to their explosive deaths, spans timescales that dwarf human existence. One might consider how long it takes for a star to fizzle out. This could take several billion years, which is a blink of an eye in cosmic terms, but an eternity in human life. Moreover, the effects of gravity complicate our understanding of time even further. Near massive objects like black holes, time behaves differently. It slows down relative to regions further away. This means that an observer near a black hole would age more slowly than someone situated far from it. These differences illustrate that time is not a uniform experience across the universe. As we expand our efforts to explore the cosmos, particularly through advanced telescopes and spacecraft that observe distant galaxies and phenomena, we become aware of the vastness of time itself. These observations challenge us to rethink not only how we measure time, but also how we experience our place in the universe. What feels like a defining moment on Earth becomes just a brief flicker when viewed against the expansive backdrop of the cosmos, compelling us to see our existence within a much larger narrative that plays out over immense periods. As humanity seeks to explore the final frontier of the universe, a variety of advanced tools and methods are taking shape to enhance our observational capabilities. Ground-based telescopes, equipped with cutting-edge technology, are at the forefront of this exploration. These telescopes utilize adaptive optics, which involve adjusting the mirror shape in real time to counteract the blurring effects of Earth's atmosphere. This transformative method allows astronomers to achieve images that rival those captured in space. In addition to ground-based observations, the deployment of space telescopes marks a significant leap forward. Positioned above the atmosphere, these observatories can capture clearer and more detailed data across different wavelengths of light, including infrared and ultraviolet. The James Webb Space Telescope, for instance, can peer deeper into space than any previous telescope, unlocking secrets about the formation of stars and galaxies that emerged shortly after the Big Bang. Radio telescopes also play a crucial role in observing the universe's less visible phenomena. These instruments capture radio waves emitted by cosmic objects, such as pulsars and distant galaxies, allowing scientists to explore areas that optical telescopes cannot. The Square-Kilometre Array, once completed, will be the most extensive radio telescope ever built and will help us delve into the origins of cosmic structures and the evolution of the universe. Furthermore, gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, are revolutionizing our understanding of the universe by detecting ripples in spacetime caused by massive astronomical events such as black hole mergers. These detections provide a new way to observe the cosmos and understand events that emit little to no light. Complementing these observational tools, machine learning and artificial intelligence are increasingly employed to analyze vast amounts of astronomical data, identifying patterns, classifying objects, and even predicting cosmic events. These technological advancements will empower astronomers to extract meaningful insights from observations that were previously too numerous or complex to interpret manually. With each of these innovative tools and methods, we inch closer to unveiling the mysteries that lie beyond our sight, allowing us to explore the universe like never before. The combination of diverse observation methods, the expertise of scientists, and the power of modern technology holds the promise of profound new discoveries in our quest to understand the cosmos. Space observatories play an essential role in enhancing our exploration of distant cosmic regions by providing a clear and unobstructed view of the universe, free from the distortion caused by Earth's atmosphere. When we look at the night sky from our planet, light pollution and air turbulence can blur and obscure our perspective. Space observatories, positioned beyond this atmospheric veil, allow us to observe celestial objects in their true form, unveiling details and phenomena that would otherwise be hidden. Observing from space enables scientists to gather data across various wavelengths, such as infrared, ultraviolet, and X-rays, which are often absorbed or scattered by the atmosphere. Each of these wavelengths tells a unique story about the universe. For example, infrared observations can reveal cooler objects like dust clouds or distant planets. X-ray observations uncover high-energy processes around black holes and supernovae. This multi-wavelength approach helps researchers piece together a more complete picture of cosmic events and structures. Moreover, space observatories can continuously observe celestial phenomena without the interruptions caused by day and night cycles or weather conditions on Earth. This constant monitoring allows for the collection of long-term data, essential for studying dynamic events such as the life cycle of stars or the evolution of galaxies over vast timescales. Insights gained from these observations can lead to breakthroughs in our understanding of fundamental questions like the nature of dark matter, the formation of the universe, or even the potential for life on other planets. In addition, space observatories often collaborate on ambitious projects, sharing data and findings with researchers worldwide. This global effort accelerates discoveries and enriches our understanding of the cosmos. As technology advances and new observatories are deployed, our capabilities to explore these remote regions will only expand, deepening our connection to the universe and revealing its many mysteries. Amateur astronomers play a surprisingly pivotal role in the field of cosmic discoveries, often acting as dedicated observers and contributors to our understanding of the universe. While professional astronomers typically rely on large observatories equipped with advanced technology, amateur astronomers use their telescopes, often from their own backyards or local parks, to monitor celestial events. This grassroots approach allows them to contribute valuable data and observations that complement professional research. One significant area where amateurs shine is in the discovery of transient events, such as supernovae, asteroids, and comets. By frequently monitoring the night sky, these enthusiasts can identify changes or anomalies that may go unnoticed by larger, more centralized observing efforts. Their findings are crucial, especially since some of these events occur swiftly and may only be visible for a brief time. Additionally, amateur astronomers often collaborate with professional teams and contribute to citizen science projects. Through initiatives that invite non-professionals to participate in data collection or analysis, they enhance the overall scientific output. Their passion for astronomy drives them to not only make observations, but also engage with online communities, sharing findings, techniques, and insights that can lead to further discoveries. Amateurs have also been instrumental in enhancing the availability and quality of data. Many utilize advanced imaging techniques and software that were once the domain of professionals. This access to such tools has allowed them to refine their observations and integrate their findings into broader scientific discussions. In some cases, their efforts have led to new theories or revisions of existing knowledge about astronomical phenomena. While amateur astronomers may not operate with the same level of resources as their professional counterparts, their enthusiasm, keen observations, and willingness to share information have made them invaluable partners in unraveling the mysteries of the cosmos, leading to a richer and more inclusive understanding of our universe. New discoveries in the cosmos constantly reshape our view of humanity's role in the vast expanse of the universe. Every time we learn about distant galaxies, intricate stellar formations, or even the basic building blocks of life on other celestial bodies, we gain insight into our own existence. For instance, consider the finding of extremophiles, organisms thriving in extreme environments on Earth. These discoveries suggest that life may adapt in ways previously unimaginable, perhaps existing even on distant planets or moons. Moreover, the exploration of exoplanets, or planets beyond our solar system, reveals that there are potentially billions of worlds capable of supporting life. This realization broadens our understanding of what is possible, prompting questions about the uniqueness of Earth and humanity. Are we truly alone, or just one tiny piece of a bigger cosmic puzzle? Furthermore, the study of cosmic events, such as the formation of black holes or the dynamics of dark matter, deepens our understanding of the universe's structure and history. It also addresses philosophical questions about creation, existence, and the future. As we delve into these intricate processes, we recognize that we are part of a magnificent universe that has its own story, one that we are just beginning to comprehend. Discoveries emanating from advanced telescopes and space missions add layers of complexity to our understanding. They challenge previous assumptions, revealing that our planet might not be the center of the universe, but rather a humble participant in an expansive, ever-evolving cosmos. This shifting perspective encourages both humility and curiosity, fostering a drive to explore, learn, and ultimately understand not just our place, but our purpose within this grand universe. Understanding the universe shapes not only our knowledge, but also our aspirations for exploration and expansion beyond Earth. As we unravel the mysteries of celestial bodies, cosmic phenomena, and the fundamental laws governing our surroundings, this comprehension becomes a critical foundation for future endeavors. Firstly, knowledge of our solar system, its planets, moons, and asteroids guides us toward potential destinations. For instance, exploring Mars offers insights into past water availability and the possibility of life, opening avenues for human settlement and resource utilization. The identification of asteroids rich in metals or even water could encourage ventures that mine these celestial bodies, ensuring sustainable supplies for Earth and beyond. Understanding the universe also enhances our technological capabilities. Advances in propulsion systems, life support, and habitat construction emerge from studying conditions on distant worlds. Equipped with this knowledge, we can design spacecraft that reduce travel time and create environments that support life far from our home planet. Moreover, as we learn about phenomena such as cosmic radiation or the effects of long-term space travel on the human body, we can develop solutions to protect astronauts during extended missions. This ensures the safety and well-being of explorers as they push the boundaries of our reach. On a broader scale, knowledge about exoplanets, what they are composed of, and their potential habitability fuels our imagination about the diversity of worlds beyond our own. The possibility of life elsewhere deepens our understanding of biology and evolution, paving the way for potential interstellar exploration. Finally, our growing awareness of the universe fosters a sense of global unity. Pursuing a common objective, such as exploring space, encourages collaboration among nations, businesses, and individuals. This spirit not only helps us share resources and knowledge, but also promotes peace. The more we understand the universe, the better equipped we become to explore it. Empowered by knowledge, humanity can embark on remarkable journeys beyond our planet, discovering new worlds and unlocking the potential for human expansion in the cosmos. As we gaze up at the stars, the idea of colonizing other planets brings forth a myriad of ethical considerations that demand our attention. First and foremost is the question of stewardship. Are we prepared to become caretakers of celestial bodies, ensuring we do not disrupt existing ecosystems? Every planet, moon, or asteroid carries its own history and potential for life, even if it's microbial. It's critical to consider our responsibility to protect these environments from contamination and exploitation. Additionally, the rights of any potential extraterrestrial life forms must be taken into account. If we encounter life, even in its simplest forms, what moral obligations do we hold towards them? The ethics of interfering with or displacing any native organisms must be weighed against our desire to expand human presence. Humanity's historic patterns of colonization on Earth also invite reflection. The impacts of colonialism, often wrought with violence, displacement of indigenous peoples, and cultural erasure, serve as a stark reminder that we must approach potential colonization with caution and respect. It is essential to engage in dialogue about who benefits from off-world colonization and whom we might inadvertently harm. This means considering the rights of future space settlers, should they have autonomy, and how do we ensure equitable access and representation. Furthermore, the question of resource utilization emerges as a significant point of discussion. The extraction of resources from other planets raises ethical dilemmas similar to those faced on Earth, relating to wealth distribution, environmental impact, and the long-term effects on the interplanetary environment. Careful consideration is necessary to determine how we can responsibly use these resources without repeating the mistakes of our past. Lastly, the philosophical implications of our endeavor into the cosmos cannot be overlooked. What does it mean for humanity to reach out for the stars? As we ponder these ethical considerations, one thing becomes clear. The journey of exploration must be guided by a framework that emphasizes responsibility, respect, and careful reflection. In doing so, we ensure that our cosmic aspirations align not only with our survival, but also with our ethical duty to the universe we are only beginning to understand. Collaboration among various scientific disciplines significantly enhances our understanding of the cosmos. At its core, the universe is an incredibly complex system where phenomena in one area can influence and provide insight into another. For instance, astronomers rely on principles from physics and mathematics to decode the behavior of distant stars and galaxies. Without these fundamental scientific tools, the information gathered from telescopes would remain largely uninterpreted. Moreover, the study of celestial bodies often intersects with geology and biology. Planetary scientists, for example, study the surface and atmospheric conditions of other planets, drawing from the knowledge of Earth's geological processes to make educated predictions about the structures found on distant worlds. This interplay informs our understanding of the potential for life beyond our planet by linking conditions that support life on Earth with those observed elsewhere. Engineering plays a pivotal role as well, especially in the construction of spacecraft and the technology required for advanced telescopes. The collaboration between engineers and scientists is vital to developing instruments that can withstand the harsh conditions of space and gather data effectively. This synergy allows us to send probes to explore far-off planets and even capture the images of black holes, unlocking mysteries that would otherwise remain hidden. Furthermore, computational science has emerged as a key player in analyzing vast datasets produced by modern observations. By employing advanced algorithms and simulations, scientists from various fields can share insights, enabling a more comprehensive view of cosmic events. This approach is particularly evident in the study of gravitational waves, where physicists, astronomers, and computer scientists jointly analyze signals to unravel the violent events occurring in the universe. Through interdisciplinary collaboration, we create a richer tapestry of knowledge, stitching together diverse perspectives and techniques to tackle profound cosmic questions. This collective effort ultimately leads to groundbreaking discoveries and a deeper appreciation of our place in the universe, revealing not just what exists beyond our planet, but also how interconnected and dynamic the cosmos truly is. International organizations play a pivotal role in advancing comprehensive research initiatives by providing platforms for collaboration, resource sharing, and the pooling of expertise from various nations. They act as facilitators, bringing together scientists, researchers, and policymakers to tackle global issues that require a united approach, such as climate change, public health, and space exploration. These organizations often fund research projects, ensuring that scientists have access to the necessary financial resources. By investing in large-scale initiatives, they enable teams from different countries to work together on shared objectives, breaking down barriers that usually impede scientific progress. Furthermore, they establish guidelines and standards that ensure the quality and integrity of research across borders, making it easier to compare results and share findings. Additionally, international organizations promote capacity building by providing training and fostering knowledge transfer between developed and developing regions. This empowerment ensures that the global research community remains diverse and inclusive, enabling a wide array of perspectives and innovations. By encouraging the dissemination of knowledge, these organizations help to ensure that research benefits society as a whole, advancing technology and improving lives. International organizations serve as the backbone for cooperative research efforts, nurturing an environment where innovation flourishes through collaboration, shared goals, and the commitment to solving complex global challenges together. The vastness of the universe poses many intriguing mysteries, from the formation of stars to the nature of dark matter. It takes a multitude of perspectives to approach these complex questions effectively. Scientists from various fields bring different methodologies, ideas, and knowledge bases that enhance our understanding of the cosmos. For instance, astronomers might specialize in observing celestial objects, while physicists use theoretical models to explain the forces at play in those very objects. When these specialists collaborate, they can see the universe in a more comprehensive way. This diversity extends beyond pure science into areas like engineering and computer science. Engineers create advanced telescopes that allow astronomers to capture clearer images of distant galaxies, while computer scientists develop sophisticated algorithms that process enormous amounts of data collected from various missions. Each discipline offers unique insights and tools, blending technical skills with creative problem-solving. Moreover, the incorporation of diverse cultural perspectives can challenge existing paradigms and inspire innovative approaches. For example, indigenous knowledge systems often offer distinct views on the night sky, which can inform scientific inquiry and promote greater respect for our universe's complexity. In scientific teams, diverse backgrounds encourage open dialogue, allowing for the testing of assumptions and fostering collaborative thinking. This synergy leads to breakthroughs that no single discipline could achieve alone, propelling our quest to decode the fundamental workings of the universe and our place within it. Ultimately, embracing various scientific backgrounds enriches our exploration and expands our collective intelligence in solving the mysteries of the cosmos. Observing distant galaxies and cosmic phenomena is a monumental task, fraught with challenges that stretch both our technology and our understanding of the universe. One of the primary hurdles is the vast distance involved. As light travels through space to reach us, it takes millions or even billions of years, meaning we see these celestial objects as they were in the past, not as they are now. This time delay can complicate interpretations of their current state and behavior. Additionally, the universe is filled with obstacles that interfere with our observations. Dust and gas clouds can obstruct the light from distant galaxies, making it difficult to gather clear images. This is akin to trying to see a distant lighthouse through a thick fog, where critical details might be hidden from view. To tackle this, astronomers use various wavelengths of light. For instance, infrared telescopes can penetrate dust clouds that block visible light. Another significant challenge is the expansion of the universe. As galaxies move away from us, their light shifts to longer wavelengths, a phenomenon known as redshift. This means that many distant galaxies may emit light in the infrared or radio spectrum rather than visible light, requiring specialized instruments to capture their emissions. Understanding this redshift is crucial for gauging how fast galaxies are moving away, and consequently providing insight into the rate of expansion of the universe itself. Furthermore, the sheer number of faint objects in the sky complicates observations. The background noise from stars and cosmic radiation can overwhelm signals from distant galaxies, akin to trying to hear a whisper in a loud crowd. Advanced imaging techniques and powerful telescopes help reduce this noise, allowing astronomers to filter out the important signals. Lastly, there are limitations in our technology. Building and launching powerful telescopes into space has brought unprecedented clarity to our observations, yet these instruments come with high costs and complexities. Each new advancement pushes the boundaries of what we can observe, but they also require meticulous planning and engineering to ensure they can withstand the harsh environment of space. Observing distant galaxies and cosmic phenomena involves overcoming immense distances, dealing with obstructions in our path, interpreting the effects of the universe's expansion, filtering out background noise, and relying on rapidly advancing technology. Each challenge presents opportunities for new discoveries, deepening our understanding of the cosmos. Exploring deep space is a formidable challenge, and researchers constantly innovate to tackle the unique barriers presented by technology and the harsh conditions of the universe. One major obstacle is the extreme environment, characterized by high levels of radiation, intense temperatures, and vacuum. To combat this, scientists develop advanced materials and engineering techniques designed specifically to withstand these conditions. For instance, spacecraft are often built with protective shielding that absorbs radiation and insulates sensitive equipment from intense heat fluctuations. Communication also poses significant challenges. The vast distances in space mean that signals can take a long time to travel to and from spacecraft, complicating real-time data transmission. Researchers have devised solutions like autonomous systems that can operate independently, making decisions and conducting experiments without immediate instructions from Earth. These systems can process data on site, reducing the amount of information needing to be sent back and forth. The power supply in space is another critical concern. Since solar panels become less effective the farther they are from the sun, researchers explore alternative energy solutions, such as nuclear power sources designed to provide a steady energy supply for long missions. This allows equipment to function even in the cold darkness of space where sunlight is minimal. Moreover, scientists continuously improve the reliability of technology through extensive testing and redundancy. By building multiple layers of backup systems, they ensure that even if one component fails, others can take over, maintaining the mission's integrity. Ultimately, overcoming these barriers requires an interdisciplinary approach where engineers, scientists, and researchers collaborate closely, leveraging their diverse expertise to create resilient and effective solutions for the challenges of deep space exploration. Their work not only expands our knowledge, but also pushes the boundaries of what is technologically possible. Advancing cosmic exploration relies on innovative technology that enhances our capabilities for accessing, studying, and understanding the universe. One area that needs focus is propulsion systems. Current technologies often limit us to slower speeds, meaning reaching distant planets or stars can take years or even decades. Developing propulsion techniques that harness energy more efficiently, like nuclear thermal or ion propulsion, could significantly decrease travel time, making missions to far-off destinations much more feasible. Another important area is life support systems for long-duration missions. As we consider sending humans deeper into space, we need self-sustaining habitats capable of recycling air, water, and food. Technologies that allow us to grow food in space or systems capable of converting waste materials into usable resources become essential to support life on extended journeys, such as missions to Mars or beyond. Robotics and artificial intelligence play a crucial role in enhancing cosmic exploration as well. Advanced robotic systems equipped with AI can operate in harsh environments, conduct repairs, and gather data when human presence is impractical or impossible. Imagine robots that can analyze samples on the Martian surface or even explore the icy moons of Jupiter. Such technology could maximize our understanding of these environments without risking human safety. Moreover, improved communication systems are vital for coordinating missions across vast distances. Current communication relies on radio waves, which can be slow and susceptible to interference. Researchers are exploring ways to use laser communications that can transmit data more quickly and securely, allowing for real-time updates and the sharing of findings from distant exploratory missions. Lastly, in terms of observation, advancements in telescope technology will enable us to penetrate deeper into space. Telescopes that can observe across a broader spectrum, from infrared to ultraviolet, will help detect celestial phenomena, identify exoplanets, and analyze their atmospheres, expanding our search for life beyond Earth. As we push the boundaries of our cosmic exploration, it is clear that each technological advancement paves the way for deeper understanding, greater discoveries, and possibly the expansion of our own civilization beyond the confines of our home planet. The universe is brimming with surprises that often go unnoticed. One captivating aspect is the concept of dark matter, which makes up about 26% of the universe's mass energy content, yet remains elusive. We can't see or directly detect dark matter because it doesn't emit light like ordinary matter, but its presence is inferred from the gravitational effects it has on galaxies and galaxy clusters. It's as if there's an invisible web holding the structure of the universe together. Another intriguing detail is the phenomenon of cosmic inflation, which suggests that just moments after the Big Bang, the universe expanded rapidly, exponentially enlarging in size within an incredibly short period. This idea helps explain the uniformity we see in the cosmic microwave background radiation, the afterglow of the Big Bang, which is spread uniformly across the sky. Consider the vast number of galaxies in the observable universe, estimated at over 2 trillion. Many of these galaxies contain billions of stars, yet it's fascinating to note that most of the universe is entirely empty space, with galaxies often existing hundreds of thousands of light-years apart from one another. This incredible emptiness also hints at the vast scales involved in our universe that can sometimes be difficult to comprehend. Additionally, there's a curious feature known as the cosmic background radiation. This faint glow fills the universe and is a remnant of the heat from the early moments after the Big Bang. Its consistent temperature across the cosmos offers invaluable clues about the universe's origin and evolution. Then there's the idea of rogue planets. These are worlds that do not orbit a star but wander through the galaxy in solitude. It's estimated that there could be as many or even more rogue planets than stars in the Milky Way. These wandering worlds could host unusual conditions and might even harbor forms of life that exist independently from a sun. The universe also operates on principles that can lead to extreme phenomena, such as neutron stars. When a massive star exhausts its nuclear fuel, its core collapses under gravity to form an incredibly dense neutron star. The density is so extreme that just a sugar cube-sized amount of its material would weigh as much as several mountains on Earth. Finally, the concept of multiverses emerges in some theories, suggesting that our universe might be just one of many, each potentially having different physical laws and constants. This idea expands the notion of reality and encourages curiosity about the nature of existence itself. The cosmos is not merely a vast expanse of stars and galaxies. It is a source of endless intrigue and possibilities waiting to be explored. In the vastness of the universe, every cosmic detail, no matter how small, holds significance in painting a broader picture of our existence. Think of the universe as a huge, intricate tapestry where each thread, representing a specific detail or phenomenon, contributes to the overall design. When scientists meticulously study these small elements, whether they are tiny particles, faint celestial bodies, or subtle light variations, they uncover patterns and relationships that deepen our understanding of the cosmos. For instance, the study of particles at the microscopic scale helps reveal the fundamental forces that govern larger structures in space. These small particles, like atoms and subatomic entities, are the building blocks of matter. Understanding how they interact informs theories about how stars form and evolve, which in turn affects the creation of galaxies. Moreover, consider the light emitted by celestial objects. A seemingly minor fluctuation in brightness or a slight change in color can indicate profound changes occurring in distant stars or even the presence of unseen planets. By analyzing these subtle signals, astronomers can deduce a wealth of information, from the composition of a star to the potential for life on an exoplanet. Additionally, small phenomena, such as cosmic dust, play a crucial role in the life cycle of stars. This dust not only contributes to star formation, but also influences the chemistry of emerging planets. As researchers examine these individual pieces, they construct models and theories that encompass everything from the origins of elements to the fate of the universe. Every small detail is a key unlocking doors to larger concepts. Each discovery, while seemingly minor in isolation, connects to others in a vast web of knowledge that enhances our comprehension of the universe and our place within it. This continuous interplay between the small and the grand emphasizes the idea that the mysteries of the cosmos are not solely found in the colossal, but are intricately woven into the minute, waiting to be explored. Recent discoveries have thoroughly reshaped our understanding of the cosmos, challenging long-held assumptions. One of the most notable findings comes from the study of dark energy, the mysterious force thought to be driving the universe's accelerated expansion. Initially, scientists believed dark energy was constant. However, newer research suggests it may not be uniform. Instead, it could change over time, hinting at a more dynamic and complex universe than previously imagined. Another significant revelation involves exoplanets, particularly those in the habitable zone around their stars, where conditions might support life. Early assumptions suggested that planets must be Earth-like in composition and size to host life. Recent findings, however, indicate that a variety of planets, including gas giants and those vastly different from Earth, could have the right conditions for life in ways we have yet to fully understand. Moreover, advancements in technology have unveiled unexpected characteristics of galaxies. Observations reveal that galaxies previously thought to be unremarkable are, in fact, actively forging new stars at surprising rates, defying the conventional wisdom that such processes should decline over time. This insight into galactic evolution suggests a complex life cycle that can be influenced by various factors, including interactions with other galaxies. Additionally, the detection of gravitational waves has opened a new window into understanding the universe. These ripples in space-time offered evidence of events like black hole mergers, which were once purely theoretical. The details of these phenomena have begun to alter previous models of how black holes form and behave. Together, these discoveries not only reveal that our universe is more intricate than we envisioned, but also invite us to reevaluate fundamental concepts about its origins, structure, and possible futures. Each of these findings pushes the boundaries of human knowledge, illustrating that the cosmos remains full of mysteries just waiting to be explored.